How's the audio coming through clearly? Great. Welcome to you all. Launching our next session here about decision support tools and models. So thank you all for joining this particular session. Our first speaker giving a keynote address is Yves-Marie Bozec. So over to you, Yves-Marie.
Thank you, and thanks everyone for joining today. So in the spirit of sharing stories, I grew up in France, on the west coast, and so pretty far from coral reefs. And my first experience on coral reef was in Egypt, in the Red Sea, and that was completely incredible. I was a student in marine ecology and oceanography, and I think I knew what was my path since then. And now I'm here today to talk about the future of the Great Barrier Reef. So I'm pretty proud to be here. What I'm going to show you today is the very last projections of the modeling and decision support team of the RRAP program. And I'd like to acknowledge all those people who have contributed to this work and thank them. So the big question we are trying to tackle here is what's the future of coral reefs, and I guess that's a question that many people can relate to, and especially because we've got very important concerns as everybody knows. First, like the effect of climate change that is accelerating and putting even more pressure on coral reefs worldwide, and also like this uncertainty around how corals are going to adapt. Can they adapt? How fast can they adapt to this rate of warming? So to do this, we need to project reefs into the future. And for that, what we need is predictive models. So I like to talk about predictive models. That's going to be my talk. But I just want to say, we know there's a lot of uncertainties around models. They are not perfect. They are not crystal balls. They not predict the future. What they give us is a range of possible scenarios for the future. And then they can be very, very useful because using those different projections, we can help better understand what are the impacts of climate change and try to assess them. And they're also very useful for educate people, the public, but also decision makers. And perhaps more importantly, they can also inform management and conservation. So this is what we are doing within the modeling and decision support group, and specifically in this sub-program of the sub-program, which is the counterfactual modeling. And the objective of the counterfactual modeling is really to make those projections, providing long-term forecast for the GBR. And that requires considering different warming scenarios. We do this to inform about future trends, but also uncertainties around those trends. And the second objective is to use these projections as a baseline to assess interventions. So typically what we will do is to simulate interventions, and to assess those benefits, we need to actually subtract the intervention by the counterfactual. One very important component, I guess, of the MNDS is to ensure that projections are credible. And that requires state-of-the-art ecosystem models, but also being able to understand the limitations of the climate models and what kind of scenario they provide to us, and being able to have a rationale around how do we actually pick climate models to project coral cover into the future. So what we have been doing, and in the MNDS, there are a range of different models. And here I'm going to be talking about Reef Mod GBR. And this model is taking probably one of the best current knowledge we've got on corals, the ecology of corals, but also the evolution and the environment of the GBR. And also taking the very last projections of the climate by climate models. And the objective here is to provide the most, trying to provide likely features for the GBR and having a criticized approach to those projections. that was the wrong button. Okay, so I'm going to give you an overview of Reef Mod GBR here. The model is individual based, so that means we are simulating individual coral colonies on a virtual space, and that space represents, this is a grid, and we design one grid for every single individual reef of the GBR, and we've got more than 3,800 of those. The model is multi-taxa, and we consider 6 taxonomic groups. There are 3 acroporids groups, one group for postiloporids, one group of large massive, and another group for catching all the rest, basically. The model is mechanistic, and we are simulating the core processes that drive the demographics of corals at different life stage. The model is also spatially realistic and at different scales. So the first scale on the grid is really accounting for spatial interactions between colonies. At the scale of a grid, we are dealing with demographic processes, recruitment, mortality, and also we are simulating the dynamics of COTS population, Acanthaceae population. At the scale of individual reef, we are capturing the effect of the environment at between 1 kilometer or 4 kilometer scale, and that includes exposure to cyclones, exposure to heat stress in the form of the heating wicks. So I'm going to be talking a lot about the heating wicks today. And it's just a very simple measure, a very common measure to measure heat stress, and has been related to coral mortality pretty well. So it's a good predictor for models for bleaching. Water quality, which is provided by e-reefs, and this is mostly the effect of suspended sediment. And we also simulate at the reef level COTS control. Finally, at the scale of the entire GBR, so more than 3,800 reefs, we simulate the metapopulation dynamics of corals and COTS thanks to a larval dispersal that connects all those individual reefs. So I'm going to explain here how the model simulates bleaching and heat tolerance. So we can navigate this graph. It's a bit complicated, but maybe we just start with the gray line, which represents the average response of a taxonomic group. And here I'm dealing with acroporid corals. And on the x-axis, we've got the heating wicks. That's the measure of cumulative heat stress. On the y-axis, we've got the probability of mortality. And then we've got this curve that is derived from empirical observation from the GBR, where, of course, mortality increases with heat stress. And what we do is, that's a very important step for modeling adaptation, is to implement a viability of heat tolerance among individuals of the same group. And the way we do is simply shifting this curve left or right, so towards increasing the heating wicks for the same mortality or decreasing. And this is represented by those the little gray spots. So then the next step is to actually simulate the transmission of those heat tolerance phenotypes across multiple generations. And this is the key of the model of adaptation we're using here, which is essentially a process of adaptation through selection. So we just start with the distribution of heat tolerance values for a group. And here, heat tolerance values can be between essentially -8 and +8 heating wicks. And heat tolerance value of 0 means that the coral colony is at the mean of the group, so basically on the green curve. When you've got bleaching, bleaching operates like a selection pressure and tend to filter out the heat tolerance, and then shift the distribution to the right towards higher values of heat tolerance. And then at the next generation, we generate heat tolerance based on this distribution and based on a parameter that is called heritability, which is a very common parameter used for selective breeding. So there are two basic, very important parameters for modeling adaptation here: heritability, that we use 0.3, and a maximum of heat tolerance. We have to bound the interval of the range of heat tolerance. If we don't do that, just with a simple action of bleaching, we'll just push this distribution towards an infinite value of heat tolerance. And those values are derived from experimental data from Palo, from only one species. All right, so how the output looks like. So the first thing we do is to run a reconstruction of the recent history of the GBR, so between 2008 and 2023. And for this, we use observed DHW, the rating width from NOAA, and reconstructed cyclones, and we use ERIS for water quality. And this is a very important process. We do this every time we run a forecast, a projection, as a first step. And it is to ensure that the model is well aligned with observations. So here the observations are the dots. They are the LTMP data from AIMS. The blue lines represent the trajectory of an individual reef. When I say trajectory, is the total coral cover, the viability of total coral cover over time. So we've got more than 3,800 blue lines here. And the red line is just the average. So it's the mean coral cover of the GBR, of the Great Barrier Reef. So now, to project coral reefs into the future, we need climate change scenarios. And for this, we use 10 climate models. And they are models coming from the last generation of models used by the last report of the IPCC. What's important to know is like climate model come with a very coarse resolution of data. So what we are using is essentially daily data of temperature from today until the end of the century. And this data is a very coarse resolution between 100 and 150K. So the first step is to downscale this data, and we use here an approach of mechanistic downscaling that takes the local physics of the reef to interpolate. To derive temperature at this scale. So we've got local temperature at 10 kilometer scale, and then the next step is from this daily temperature data downscale at 10 kilometer is to estimate the rating weeks with the common algorithm of the rating weeks. And finally, we interpolate these values at the reef level. So for every single reef, we've got a chronology of the rating weeks from today to the future, to the end of century. Each model comes with different scenarios of climate change, and we're considering here 5 scenarios. So they are called shared socio-economic pathways, and then they represent some expectations about the future of the carbon economy. They come with very different expectation of warming by the end of the century, and you can see this, plus 1.5, plus 2, 3, 4, or 5. And those scenarios have different likelihood, and people tend to actually agree that the most likely scenario today is the one that is called middle of the road, and that which assumes that there's going to be a warming below plus 3 degrees by the end of the century. So I'm going to be mostly describing this scenario. I'm going to show you projections for the 5 scenarios, but I will mostly develop this particular one. Just one further step is like with each climate model, we come with only one projection. So in order to create a bit of variability between projections, what we do is reshuffling each chronology within a decade. In order to create, for each model, we are creating 20 new chronologies of the rating weeks. So we've got more stochasticity in our predictions of bleaching. So from 10 futures, we actually derive 200 futures that we can use to project coral cover. And the very last thing we take care of is like we need to realize that not all those models have the same probability, are not equiprobable. People have been describing and useful metrics for comparing this model is the climate sensitivity, which really measure how sensitive those climate models are to those processes of warming. And models with high values of climate sensitivities tend to actually predict warmer future than others. And those apparently are less likely. So this curve represents the density of probability associated to different values of the climate sensitivity. And we are using this probability density to resample our set of 200 runs based on this relative likelihood. So we can to give preference to climate models that have greater likelihood than others. Here I'm just showing one sample forecast. This is one run using only one climate model for one warming scenario, which is 4.5. What? Wow, okay, so I'm not going to show that. I'm going to go directly to the results of the predictions for all the warming scenarios. So first, I'm showing the category of decreasing weeks that will be that are projected to occur on the reef. Here are the simulations showing the mean coral cover for the entire GBR, and there are 200 of those, right? And you can see there is a great variability among climate models. And here, this is after resampling within this set of runs according to the likelihood of those climate models. And we represent this as a distribution for every year of the mean coral cover of the Great Barrier Reef. And those boxes, the boxes cover 50% of the data, and the central mark represents the median. As you can see, under this scenario 1.9, which is the most optimistic one, we start losing coral cover early on until the 2040. Before there is a kind of a rebound, and we think this is due to the fact that corals tend to adapt and can recover from this warming. Here I'm representing the average coral cover in the past 15 years as a reference. So you can see that with this scenario, we can maintain coral cover into the future with the same at the same level, basically. 2.6, which is still quite optimistic. We've got a bit more bleaching, a bit more viability among multiple runs. But pretty much there's a good outlook. Like even though we lose corals in the first 10, 20 years, coral tends to rebound after that, probably due to the potential of adaptation. So the most likely scenario is 4.5, and as you can see here, there's a big difference in the intensity of bleaching occurring over the century. And that really gives a different outlook where coral cover basically declines strongly and with no scope for recovery. I'm not going to detail the other scenarios because they are less likely and it's just getting worse and worse. So I think it's a bit depressing. I'm just going to focus here on the most likely scenario, 4.5, so 3-degree warming by the end of the century, just to show you that all species are actually affected by bleaching. Here I'm representing on the left the more heat sensitive, so the acroporids and posiporids, and on the right the most tolerant ones. But even the more tolerant ones tend to decrease over time, which will be different under 2-degree warming. And especially the first group, the heat-sensitive corals, which also are the fastest growing corals. You can see really like this rebound is really due to the potential to grow after disturbances when they get adapted. We can look at the density of coral juveniles, and under 3-degree warming, we can see that basically there is a constant decline of coral juveniles, which reduce the scope of recovery. But interestingly, if you look at the 2-degree warming, there's a kind of sustained ability to recover with density of juveniles that's not changing much over time. If we look at the individual reef scale, there is great variability of the responses, and this variability basically reflects thermal refugia across the GBR. But what's important is with this most likely scenario of 3-degree warming, these thermal refugia tend to vanish over time, so that by the end of the century, there is no real thermal refugia anymore, which won't be the case under 2-degree warming. Of course, there are some limitations of the model, especially with the model of adaptation, because it's not a model of adaptation based on explicit genetics. There are processes we are not considering here, like mutation, acclimatization. There's only one trait under selection, which is probably an oversimplification. If there were multiple traits, that would provide a different rate of adaptation. Heat tolerance is informed by only one species, with a big limitation, and probably the most important parameter, the critical one, is the maximum heat tolerance that we put as a limit. Just to show you very, very quickly here, is for those two scenarios, how actually heat tolerance evolves over time. And you can see that they tend to plateau. The average is around 6, but you can, at the reef level, you can go up to 8. But with a higher maximum heat tolerance, it's very likely that we will get higher adaptation potential. So this parameter is absolutely critical, and we don't know much about it. And also, we're not considering other impacts such as ocean acidification. So in summary, just to finish, assuming 3-degree warming is the most likely scenario, there is an escalation of heat stress, more severe, more intense, and a generalized decline of coral cover. And this is because basically warming, the rate of warming exceeds the potential of adaptation. The thermal refugia just vanish, and all coral disappear. Not disappear, but decrease strongly, and there is very, very limited capacity to recover. Under 2-degree warming, which is getting less and less likely, we're losing this opportunity. But there's great difference, right? The reef keeps being resilient and with adaptive capacity that allows it to recover. And that should be, I think, an incentive for reducing carbon emission with global actions. If not, I guess this sets kind of ambitious goals for management intervention. And I'm done. Sorry.
Thank you, Yves-Marie. We have 5 minutes for questions.
Thanks, Yves-Marie. Really, really interesting. Question on one of the ensemble slides. I think it was for SSP 3.5, but there was 2 clusters. So as you go out from kind of 2050 to 2100, there's like seems to be like 2 clusters of results. One very low and one a little bit higher. Do you have any thoughts about what's going on there?
Well, that's the difference between climate models, essentially, yeah. Some are more optimistic than others. Yeah. I haven't represented the gray lines represent like the GBR mean for each climate model. And they tend to actually cluster, like there are like 3 or 4 models that are much more optimistic than the other ones. That's what we're seeing here.
Thank you. And just a reminder for questions, if you could move to the microphone at the back. So another question? Just so the online audience can hear.
Yves, I'm trying to look for something positive in the 3-degree warming scenario. Does the southern extent of the Great Barrier Reef extend further south? And so is there anything positive about that?
This is not considered in our model. Our model stops at the southern GBR, and I guess what's further south is potential for new colonization, but for new construction of a new reef, I think we're going to have to wait for decades.
Yeah. Okay. Just I've dived off Brisbane, just to the north of Brisbane, and there is coral there. I mean, this is 10 years ago, and so I was just hoping that that might give some positive.
It's a good hope. Yeah. Hopefully it keeps going, and we start seeing a reef building from that. But it takes a long time.
Thank you.
Thanks.
I wonder if you've done some hindcasting and compare your model with past occurrence or what happened in, for example, the Great Barrier Reef, and if you've also tried to disentangle the combinations of the different stressors, like how they combine. Is that additive or synergistic? Particularly, for example, degree heating weeks plus cyclone and so on.
Yeah, so it was part of a study that we dedicated on the handcasts, where we did reconstruct the past 15 years of corals across the GBR. And we used this model to try to estimate the relative contribution of different stressors. And what we found is cyclone was still a big driver, but bleaching tend to actually being one of the most important driver in the past 15 years compared to COTS and cyclones. So it's likely to continue getting even worse than that. Yeah.
So we have time for just one more question. So I think you put your hand up there.
I think it's a very quick question. The deep valleys we see in that diagram over there, are they the cyclone impacts, or what's that?
It's actually disturbances, likely cyclones or bleaching events, and most likely cyclones, I guess, at the end of the century, yeah, because you can still see a lot of corals, and they just, that's the effect of a cyclone.
But they are stochastically allocated, so it could be.
Right, so this
other
is one.
years or-
This is one sample. So if you use another one for the same reef,
It
you
will
will
be
see a
somewhere
different picture, because the cyclone will occur before or after, and the same with bleaching. Yeah.
Thank you.
Thank you very much.
Thank you, Yves-Marie. I'm sure he'll be available for more questions at lunch to follow up. Our next speaker is Peter Fitch from CSIRO. Thank you, Peter.
Thank you. Hi, everybody. Complete change of gear for me. I'm going to talk about the information system that has been put together to support the modelling and decision support work. But first of all, a little bit about me in the spirit of sharing something. My first encounter with reefs was actually when I was a 10-year-old off the coast of Kenya. And I remember seeing crystal clear water and very colourful reefs, and that was added to, I was very fortunate and grew up, had the chance to spend a lot of time in the Solomon Islands. So from when I was, again, about 10 to 18, I'd go to school in Australia and spend my school holidays in the Solomon Islands. Beautiful water again, amazing reefs, and so I feel, like a lot of you, an affinity with the warm tropics and the colour and the wonderful wildlife of the reef. So a little bit about me. So I'm going to spend, as I said, a little bit of time talking about. Okay. Talking about two pieces of work. The first one is, I guess, in the program's wisdom. It was identified that an information system would be super useful, if not imperative, to supporting the work of the modelling and decision support team in understanding, I guess, the counterfactuals and assessing the options of interventions in a systematic way, moving towards the production of an operational system. So an early piece of work was to really put some thinking into the design of what that information system might look like. And we produced a report called the RRAP Modelling and Decision Support Design Report, which was really a conceptual framing of what we wanted to do with that information system and how those different capabilities could be brought together to support the objective, which was quality decisions, ultimately deciding what some of those intervention options are going to be for the reef. It's worth noting that a very early use case was this one of kind of trust and also justification, where we felt that at some point down the track, the question would be asked, well, how did you make that conclusion? What evidence did you use? And so this idea of provenance and trust weaves through this. The aspiration, of course, was quality decisions, and we didn't know what the endpoint was, and so we went about it by establishing a set of principles, conceptual frameworks, key artefacts and some suggested processes to support that ongoing need for quality decisions. It's fair to say that designing IT systems is hard at the best of times, but designing IT systems that support transition from research to operational capability is absolutely challenging. We're in a landscape where IT fail is very common, and transitioning, I've been involved in a couple of quite large programs where the objective is transitioning research to operational capability, and that has been a very challenging place to work as well. It's not just us in Australia, it's a global issue. And this model here is, it's actually a little bit old now. It's 20 years old, but this is about transitioning research from NASA, where they developed the remote sensing capability, into NOAA, where the capability was to be operationalised. And there's two key transition barriers that need to be overcome. The first one is getting the research out of the research teams and into the operational providers, and there are challenges associated with that. And then getting the capability from the operational providers to the operational users, so the end stakeholders and two valleys of death. So I think where we are at the moment in that journey is probably we've crossed that first transition to varying degrees, and we're getting the capability in the hand of these operational providers, but there's still a job to do to move that capability into the end users. As I mentioned a little bit earlier, the way we approached this, given that we didn't know what the end target was to put together some conceptual frameworks, some principles, and some process around that. So I'll just briefly tackle a couple of those, one in a little bit more detail. The decision framing, which defines how quality decisions are made, was kind of put together, and this really described the framework theory and how those quality decisions would be made. The knowledge framework identified the types of knowledge that would be captured by the information system, and the technical framework, which I'll go into a little bit more detail, really describes how it was put together. The principles are really associated with agile improvement. So knowing that each time you put something together, it's not going to hit the target, but you work your way through in a prioritised, systematic way to improve the information system. And this idea of continual improvement through maturity assessment, having documents like a technical strategy and active groups that implement that strategy is a key part of producing the system as well. In terms of the, in terms of the conceptual view of the information system, we recognise three main viewpoints. One is what we call the enterprise viewpoint. This captures the business needs, so supporting what decisions are going to be made by who and why. This then leads to two other viewpoints. The next one is the knowledge and information viewpoint, which answers key questions like what models do we need, what data, and what information to support quality decisions. And lastly, the technical viewpoint, which is how, from a technical point of view, is that system going to be put together and overseen by on the right-hand side there, I think, the RRAP Governance Technical Committee. So this is what it looks like. On the right-hand side there, we've really focused on the capability to support the program around registering and retrieving data sets. And so you can see the data store in the information system, which is called Pravina. And underneath that is the provenance store, which stores information about how those data sets were used, how the modelling results were generated. And this provenance store can be queried, so you can understand the lineage of those modelling results to generate trust in the outputs. We're focused on supporting three main groups. The main group that the information system is supported at the moment is the internal team. The modelling and decision support team are the main users of the information system at the moment, but we're imagining as it moves to operational capability, ultimately other researchers and decision makers who are charged with the responsibility of determining what interventions are going to be invested in. So the uptake and use has been pretty significant, and we use this as evidence of kind of the mainstreaming and as I said at the beginning, where we are in that journey of transitioning to an operational capability. There's about 73 data sets registered, 38 model runs registered, 14.3 terabytes of data sitting on the IS, which is huge. Data in is around about 4 terabytes over the last 12 months, and about only half a terabyte has been extracted. So it looks like the pathway into the information system at the moment is much stronger than the information out, but I think that is consistent with where we are in that operational journey. We've got this continual improvement process as part of the original design, using this idea of a maturity model, which is again identifying things like what's best practice, where are we relative to that best practice, and what should we prioritise to improve. We performed the first of these maturity assessments recently. Just quickly on this slide here, on the y-axis is a definition of what operational capability is. On the column headers, they are levels of maturity with, I've got to get this right, with more mature being on the right-hand side and less mature on the left-hand side. And we note there that any of those operational capabilities that are implemented with the information system, which is on the right-hand side there, automatically have high level of maturity. So what that means is, in terms of having a robust operational capability, if the information system is used by de facto, you move to that high level of maturity. So, critique and key messages. So, we think that design report and conceptual approach, along with methods, has actually served the program very, very well. We also say that it's driven the maturity improvement, and as teams have increasingly used that, it has improved the maturity of our operational capability. We say that the information system has been critical to developing and transitioning that pathway to operations. And I think the maturity assessment that I showed previously, and there's others behind there, have really validated the approach that we've taken. Transitioning is ongoing, and the call to action is to really encourage the teams in RRAP to continue to use the information system. I think it's a real core asset that we have, and will place us in a very good position as we move to making the broader set of capabilities available to other users. Thank you.
Thanks, Peter. We have 4 minutes for questions. Are there any coming in online in the Slido? No, not at this point. Thank you.
Hey, thanks, Peter. This isn't a canned question, but it is something I've asked you before, asked Jonathan and others that are involved in this before. So this is awesome for RRAP. There are other programs on the GBR that would like to start making use of this type of technology, like the CSIP stuff that we're working on. How soon do you think it would be available for other programs to kind of reuse in a format similar to what you've already got running for RRAP?
Yeah, so thanks, Cameron. The answer is I'm not sure, and I guess like a lot of these things, there's a range of different drivers here, but at the technology level, it's been implemented with a technology called infrastructure as code. So the whole system it can be built very, very quickly through this code-based definition. And so if different instances of the information system were required by other teams, then that's quite a feasible proposition. In terms of everybody coming on board with the existing IS, which would be awesome, I guess that's from a program point of view to establish if that's a goal, because at the end of the day, these systems do require funding and maintenance and support. But I do think from a system point of view, there are no barriers to that. It's probably more from a program and political point of view.
Time for one more question. Okay, thank you, Peter. So we might just pause for 1 minute in the interest of staying perfectly on time. I could talk a little bit about the conference overall if people are keen. Yeah, Barbara, thanks.
There's so many great talks going on, so we'll be missing some we'd like to see. Is it being recorded so we might be able to catch it later?
Yes, so everything was being live streamed and recorded, so you'll be able to view after the event. We're also hoping the panel discussions at the end of the day will help share knowledge across the different sessions. So it's always an issue at symposia like this. There's going to be some points where multiple talks are on at the same time that we'd all like to watch. Okay, our next speaker this morning is Pedro. Is Pedro available? Thank you, Pedro. Welcome.
Good morning. My name is Pedro, and I hope to present to you how to use scenario analysis to extract rules with a tool called SIRUS to explore resilient reef futures. This work was done with the help of Takuya Iwanaga. We both work at the decision support team at AIMS. And before I start talking about scenario discovery, I need to talk about what is a scenario. So the scenarios to us are future states of the world, but because we don't know what is a future, we are talking here about a model. So the future is the future predicted by a model. That depends on a few factors. So those factors can represent something we cannot directly change, like environmental factors, but they can also represent something related to a decision or intervention, like how many interventions, when do we start, the frequency, etc. And we can run this model many times, simulating different interventions, also different environmental possible futures. And this way we can generate many scenarios. But the question is, how can we use this model to make better decisions for the future if there's this great range of possible different futures that the scenario predicts? And to this, we are going to use time series clustering together with SIRUS, which I'm going to present next. So the first question is, how can we compare different scenarios? One way will be to use the output of the scenario at some point in time and group together the ones that have the same value. But this is not very trustable because this choice of points in time, so 20 years from now or 10 years from now or 100, is arbitrary, and the scenarios can change a lot, the behavior during time. So depending on this choice, you have different groupings. This is not very trustable. Another way will be to use some metric based on the scenario, like the average value. But again, this is not very trustable because you can have, for example, two scenarios that behave very differently and have the same average value. So you will group them together, but they actually are not alike. And that's why we can use time series clustering. So on the left-hand side, you can see many scenarios generated by a model. And on the right side, the result of applying this time series clustering algorithm, which groups together scenarios based on their time behavior. So for example, here you can see a group of scenarios that have a big drop at the beginning and they are steady, or the ones that have higher values than the others overall, or the ones that are wavier than the others. So this way we can choose one of these groups, for example, the ones that behave better than the others, to target and investigate what is happening there. Just a quick overview of why can we do that, how can we do that. There's something called complexity that captures the behavior of the scenario. So this complexity, I don't know if you can see, but it's just the sum of the variation of the scenario over time. So you can see that if the scenario changes a lot, this complexity will be bigger. And then when you divide one by the other, you have a quotient that is the comparison between the behavior of both scenarios. If this number is close to 1, that means that both scenarios kind of behave similarly. Otherwise, if this number is bigger than 1, it means that one of them oscillates much more than the other, and that's how we can compare two scenarios and take into account this time behavior. And this is the result using Adria, which is the software we developed at Ames. This is just demonstration data, not real data, but just to show an example of how that works. So this is 4,000 scenarios generated by our model. And on the right side, 6 groups created based on these scenarios, changing again the possible intervention factors or environmental factors, biological factors, etc. So this is the big picture so far. We have a model, we can generate many scenarios, and we can group those scenarios by behavior. Now the next step is to interpret. How do we make sense of this? And to explain that, I'm going to use an analogy with the Titanic data set. So this is a data set containing information about more than 500 people on board of Titanic. We have information about their gender, age, type of ticket they had, etc., and if they survived or not. And the question here is not to predict if they survive or not, because we have a lot of prediction models out there. The question here is which information is more relevant to determine the survival rate. So we are interested in knowing if let's say you have a person and I know this person is male, is this information relevant as a predictor of the survival chance? Or maybe knowing the age of a person is a more relevant information as a predictor. So that's what we want to know. Not a prediction model, but which characteristic is more relevant as a predictor. And we use SIRUS for that. This is why we use this algorithm called SIRUS. This is an example of what SIRUS does. It creates those trees, those decision trees, randomly. So each time it selects 2 characteristics from the list that we have and a small group of people, and it builds thousands of trees like this one. They will be slightly different. And for each tree, we can extract a rule that is highlighted in this yellow box here. This rule, for example, if a person has a first or second class ticket and is female, then the survival probability is 95%. This rule contains the same information in this tree, so this rule was extracted from the tree. And by creating thousands of trees like this one and extracting thousands of rules, SIRUS can find the rules that appear the most, that are more relevant. So this way we can make sense of this data. On the right side, just a scatter plot with, again, the same information. So the gray area is the one selected by this rule. Each dot is a person. The blue ones are the survivals, and the red ones are the non-survivals. So just another way of looking at the same information. And going back to our example, now instead of trying to predict if someone is going to survive or not, we are trying to predict if a scenario is going to be in the target group or not. So from our 6 groups that we created based on their behavior, we can target one of them and try to see which factors are more relevant as a predictor of a scenario being part of the target group or not. So just an example of a rule extracted by SIRUS. In this case, it is saying that, again, highlighted in the yellow box, if factor A is greater than 2.3 and factor B is greater than 21, the probability of the scenario being in the target group, in other words, behaving like this target group, is 80%. This is relevant because, again, factor A and factor B could be related to some intervention, like how many deployments of something we do, or with which frequency, or when do we start. So we know that from all the things we can change about that policy or intervention, those 2 factors are very relevant to determine if we do that thing that way, the system is going to behave, or the future is going to look like the scenarios inside this blue area in the target group. So this is the big picture. One thing we can do with that is do it again. So we can do this same thing in cycles, running more times the model, generating many scenarios, simulating other possible policies and interventions and ecological factors, etc. But most importantly, we can use that to inform discussions and policy and management decisions. That's all. Thank you for listening.
Thank you, Pedro. We have time for questions. Open it to the floor. Thank you, Scott. Wait, Rail's bringing you the microphone.
That's all right. So the clusterings you were looking at were, I think you were saying, were driven partly by the different interventions. But do you get clusterings that are more to do with the sort of stochastic environmental forcing? So if you have a scenario, say, that happens to have just stochastically lots of cyclones over a period, it might cluster differently to another set of scenarios that just stochastically didn't have too many cyclones.
Yeah, so every time we run a scenario, so when I say we have many scenarios, for each scenario, we are changing environmental factors. So we have, in this case, the possibility of changing stochastically the cyclones, degree hidden weeks, other environmental factors, also biological factors, because there's an uncertainty related to that. So each scenario, we are varying all those things. So when we cluster, the cluster contains both environmental and biological and decision-related factors, everything together. Yeah.
Thanks, Pedro. 2 questions. First is on the time series clustering. There are systems that bifurcate. There are like multiple steady states. And I wonder how your classification will perform, given that those like bifurcating system, they're really like the signal of a single like driver. The second is on your SIRUS. Is that like a statistical analysis, and is it related to a boosted regression in that's used usually in ecology.
Sorry, what analysis?
Boosted regression, the SIRUS. I wonder if it's a new statistical analysis or it uses like boosted regression as a...
Okay, I'm going to answer the second one first. So SIRUS uses random forest, sorry. So that's the idea. It's basically a random forest algorithm. It's the basic idea. You build many trees. The difference is before building the forest, it uses as split points the same split points. So for every tree it builds, the possible split points are always the same because they are the n quintiles. So let's say you want 7 fixed split points. So you have the 10, 30, 50, 70 quintiles. But other than that, it's basically a random forest. And about the first question, what I think will happen is that because when you say a system bifurcates, to me it will be like a few scenarios will go one way and a few will go the other way. And in this case, it will select 2 different clusters for this. Yeah.
Can you explain, Pedro, what's the advantage of having the predefined split points rather than just letting them emerge?
Oh, yeah, of course. This is why the algorithm is called SIRUS, and this S in the beginning is for stable. So if we just use a random forest algorithm, every time we add more points, so let's say in the Titanic case, if we found out 10 more people aboard the Titanic that we forgot, and we add those people in the data set, the rules extracted by the random forest will be slightly different. With SIRUS, when we fix these split points using the quintiles, if we have new data or something like that, or if you just run the same algorithm multiple times, the split points will tend to be the same. This is the stability. So is it stable under new data entering the data set?
Sorry, in the interest of time, we need to move past the next speaker. Thank you so much.
Thank you.
Okay, thanks everyone. Our next speaker is Scott Condie from CSIRO. Thanks, Scott.
Thank you. Okay, so now we're sort of moving back a little bit to the sort of modelling that Yves told us about during the keynote. Although it is a different model, and we'll be emphasising more the role that reef fish play in those sort of systems, and particularly in terms of their predation on Crown-of-Thorns starfish. So I just want to acknowledge the traditional owners, and in particular, because I'm based in Hobart, the Muwina people were the traditional owners of the land that I work on. So this is a CSIP project, and the objective really was to look at evaluating the efficacy of fish conservation strategies in controlling Crown-of-Thorns starfish outbreaks, and therefore what benefit that might bring to corals and thus the entire community. And as I mentioned, we're using for this another reef meta-community model to explore scenarios. So the underlying idea of what we're trying to do here is this idea that certain reef fish prey on Crown-of-Thorns starfish, either in their juvenile or adult phase, and therefore that if they're preying on the Crown-of-Thorns, then that's going to reduce the predation pressure on corals, and therefore obviously improve the state of the reef. And we're focusing mainly on two types of reef fish here: the emperors, things like spangled emperor and red-throated emperor, which are known to prey on Crown-of-Thorns starfish, and also gropers like coral trout, who don't prey directly on Crown-of-Thorns, but there's an interaction there through the food web. And you can see if we're changing the level of fishing and thus the populations of these predatory fish species, then that's ultimately going to impact on crown-of-thorns and corals themselves. Okay, so the model we're using for this is known as the Coral Community Network model, or COCONET. This model's been around for a while now, and probably some of you are familiar with it. It's somewhat similar to what Eve talked about with their reef model, but there's also, I guess, almost purposeful differences. So the structure of the model is different in various ways, and we try to maintain those differences to give us, so that we're sort of better capturing the uncertainty when we're applying kind of a multi-model ensemble to different problems. And so, similar to ReefMod, it contains multiple coral groups. There's 6 coral groups that vary from fast-growing sort of acropora type things through to massive corals. We also have an age-structured COTS population preying on the corals, and one difference from ReefMod is that we have these age-structured fish populations, which are explicitly represented. And on top of all that, we have the environmental impacts such as cyclones and marine heat waves, which are obviously impacting the corals. And we also have the human activities. So this might be control of crown-of-thorns starfish, or line fishing, which is obviously reducing the fish in the system. And we can also explore, various other interventions in the model. And because it's a meta-community model, so we're representing all these individual reefs down at the scale of the COTS control sites. So that's sort of like a 10-hectare type scale. But all the reefs are interacting through spawning events of coral, of crown-of-thorns starfish, and of the predatory fish. And you'll hear more about the sort of connectivity aspects in talks later in this session. So the sorts of interventions that we're trying to model here range from modifying the zoning. So as you probably know, on the Great Barrier Reef, we have green zones and blue zones where the fishing is not allowed on the green zones, and so we can vary how many reefs and which reefs are zoned in certain ways. We can just look at fisheries management strategies such as reducing catches. We can impose size limits on the fish catches. So at both ends, we could protect the larger fish or protect small fish. Getting a little bit more speculative, we can stock, restock reefs with some of these predatory fish. That's not happening at the moment, and it's probably pretty challenging, but it's kind of interesting to look at in a modelling sense. And of course, the control program itself, we can also model. And there's other talks that are going to be detailing that more as we go forward. The way we run the model is we essentially we actually started in around 1900, and we have this kind of 70-year equilibration period. So you just it doesn't really matter how you initialise, but all the reefs are initialised with the various populations, and then we allow quite a long period for this whole system to come into equilibrium, and then we model a historical period, through to present day essentially, and this is also the period over which we calibrate this model based mainly on LTMP data, that's long-term monitoring program data, and then once we have that calibration in place, the models then run out over a projection period, which goes up to can go in anything you like really, but out to 2075. And that's quite a long projection, but you've got to remember that underlying this, we've got, the time frame for COTS outbreaks is like, 15, 16-year frequency. So we want to get multiple COTS outbreaks within our projection period. And this whole thing then is run on a large ensemble, because there's all this uncertainty in these models and lots of stochasticity. So we run it over and over again, in this case 30 times, to sort of get a handle on how much variability there is in the model. And if we look at the an example of the output, now this is a kind of interesting case where we say, well, what's the difference between what's happened historically in terms of imposing, the management regime in terms of our zoning and our management of fisheries? What's that look like relative to if we'd done nothing, if we just let things play out? And as you can see here in these plots, these are essentially showing quartiles over time, going from around 2000 to 2075. There's obviously a large benefit to fish, and consequently the number of outbreaks drops quite substantially. You can see again there's plenty of uncertainty there, but there is those trends, and then there's a net benefit to coral cover as well, and a substantial area of coral has been gained through those interventions. So it's sort of confirming that was a very worthwhile process. Now, if we look at some of our other scenarios, the black line at the bottom there, so this is the percentage point change in COTS outbreaks, and the plot, the black line at the bottom there is the one I just showed you. So the difference between historical versus if we'd done nothing, and you can see there's a very substantial change in that case. These percentage points, remember, they're not just a percentage increase. So if we get a drop by 4 percentage points, that's and the percentage of outbreaks at any time is only 10%, then that's sort of like a 40% improvement in the situation. And you can see, it's pretty much what comes out of this is quite hard to change it substantially beyond what we've already achieved. Stock replenishment for emperors is substantial there, but as I said before, that's really quite difficult to do. And now if we look at the subsequent change in coral cover from the same set of scenarios, again, what we've done previously has been, a huge benefit. 2%, 2 percentage point increase in coral cover, but if we had 20% coral cover initially, then that's still a 10% increase in total coral cover. So, that's very worthwhile. And there's some other things that, it's quite variable over time. But if you look out, later on, in the later part of the time period, then what comes out is that probably things like COTS control are still our best bet going forward. So just a point on, so why is it difficult to make these additional gains? Partly it's because COTS account for less than half coral mortality, so there's a lot of other things going on in the system around, cyclones and bleaching and so on. And the other thing is that the nature of the outbreak, we can implement things and change the nature of the outbreaks, but we don't necessarily always have a big gain in coral cover, because we might be going from, pushing the system from acute outbreaks into more sort of a chronic level of COTS over the system. So just conclusions. So the rezoning that's already happened and the fisheries regulation has clearly, at least according to the model, significantly enhanced the health of the GBR. We have marginal benefits from further expansion of zoning or reductions in fishing, so we're into that sort of diminishing returns. COTS control may provide more reliable gains over the longer term, and we're going to hear more about that in some of the future talks. And just something to keep in mind, all these runs were conducted under essentially the Paris target sort of scenarios. And as Yves mentioned, that they're probably a little bit optimistic. So we chose those because we wanted to see the signal from changing fisheries management, etc. But it might be even harder if the climate scenario looks worse. Thanks.
Thanks, Scott. It's great to see the sort of progression of this work. It's been going for a while. It's awesome. Your penultimate slide, you actually talked about the acute versus chronic kind of outbreak pattern. Certainly something we've had lots of discussions about. I mean, partly from a management point of view, it may be easier to manage a chronic pressure for a whole variety of reasons than an acute one. Yep. I just want to know whether you've actually been able to model that as to what the kind of impact profile actually is when you've got this chronic ongoing pressure as opposed to these sort of peaks or booms and busts in the COTS outbreak cycle.
Yeah, well, the way the model works, we don't actually impose that. That's just an emergent property of the model, and we've seen evidence suggest that is what the model suggests does happen, sort of thing. So I think you're right that if there's other things in the model like COTS control, then they are more effective at dealing with that just on a capacity basis, because if it all happens at once, you can't. It's hard to do much with. I guess the only context that we've looked at so far is in it just emerges out of the model and it is what what it is kind of thing. But it's an interesting part of the problem, and I think probably in other systems, I think even Japan and things they've seen this sort of effect where you do move from a more acute to chronic impact. So something to keep in mind when we're trying to manage these things for sure.
One more quick one.
Well, it's not that quick. I guess I'm just curious. I've been a bit cautious with both this model and reef mod. I've been thinking for quite a while that the big thing that drives all the trajectories and whether or not a certain strategy is going to be effective is how sensitive it is to bleaching mortality, really. And the thing I've sort of come to realise is that it's all based off the one bleaching assessment that we have is at quite shallow depths. And I'm a bit concerned that we're being potentially a bit over-pessimistic. I'm just wondering if you've got any ways to account for it, because there's been a few, like the 22 and 2020 bleaching, both like totally understandably why they were over, like the mortality was overestimated, and the one going on now probably be a different story. But it just concerns me a little bit that we're running it out so far, and without updated mortality assessments, we're potentially going to be throwing away ideas that might offer benefit. So that's not really a question, it's just a thing that's been on my mind for 2 to 3 years.
No, fair enough. And I mean, that, as I said, that's the exact logic why we chose Paris and not maybe what Yves talked about as the most likely scenario. Because there is this, bleaching is one thing, but what is the ultimate bleaching mortality is a huge source of uncertainty in these models. And I noticed it even in the modelling where we try to reproduce the recovery that we've seen in coral over the period that we've also seemed to have had the most bleaching events, so from 2017 onward. That's actually, the model sometimes struggles with that just because the recovery is so fast when all this bleaching is supposed to be happening. It's telling us that uncertainty is really important. And what our strategy is to try to not over-emphasise that.
Yeah, that's a very
climate,
fine line because
climate
you don't want to
signal,
underrepresent it as well.
so we can't see anything else. Thanks. So. Thank you.
Thanks, everyone. We're now moving to a phase of the session where we'll be talking about connectivity, hydrodynamics, linkages among locations. So our next speaker is Severine Choukroun from James Cook Uni.
Thank you very much. I'd like to acknowledge the traditional owners of the land where we meet today and of the place where I work in Townsville, the Bindal and Bulgur Kaba. So we've just been talking a lot about metapopulation, and it's mentioned that, yes, they're all using dispersal in the background. And so that's what I'm actually going to talk to you about now. So as part of the decision making, and it was done during the 2004 rezoning of the GBR, it was actually talked about that biophysical modeling and better understanding dispersal was really important to, well, that's what they're explaining with where are the corridors, where is the migration, and how we should actually support that. However, in 2004, we didn't have the capability or the modeling that we're having now. So this was kind of the idea, and now actually dispersal is being used to make decision, and that's a bit difficult to talk about it with Sam in the room, but so for COTS, please feel free to correct me if I make any mistakes, but for COTS control prioritization, actually now dispersal is 2 of the 5 key input that comes into the decision. Thank you very much. And that comes to a value that is the ecological value, and there also a tourism value. If you've got any question, you'll have to talk to Sam exactly about how it comes up with using all of these inputs and just making. But this is used to actually make a list. So every year they go through the process, and they make a list based on what are the reefs that they should prioritize based on where the COTS are, what reefs are going to be affected by them due to dispersal. So that is something for Sam. But I wanted to just step back a little bit and say what is actually needed to understand dispersal. And this is pretty much a 3-step work. The first step is to understand what is happening on the reef. What are the ocean currents doing? So that's your first step. You need a hydrodynamic model that is actually going to show you what's happening around the reef. The Great Barrier Reef is extremely complex. So you're going to have some trouble depending on what you are actually going to resolve. What are the processes that you're going to resolve depending on the type of model that you're going to use. And so these flow fields that you get from this model are being used to actually drive your trackers, your particle trackers. That's where you set all of your, when is the spawning happening? So you start driving, so you go from a Eulerian world to a Lagrangian world, where you're actually moving your particles with the currents. And then the third step, and it's where you have even more variability, is what do you know about the biology of these little larvae? Do you really know when they are going to be spawned? Do you really know where they travel in the water column? Do you really know when they're going to be competent to actually settle on the reef? And so that's your last, when you're actually getting your connectivity matrix. And this is actually the input that is being used for the reef prioritization, but also inside a lot of the metapopulation model. So in our project, what we thought was, okay, we probably need to do a bit of a review. What do this model actually represent? And so our aims was to evaluate the model prediction. What is the uncertainty that is coming from the hydrodynamic? What is coming from the uncertainty of the biology? So one way of dealing with it is doing some sensitivity analysis. And how do you transform this information to be the best key input for management? So the method that we use is we kind of got a bunch of people together, so key expert in their field, and so in hydrodynamic modeling and trackers, but we also got a lot of the ecology and biology. because we needed to also update, so integrate the knowledge that has been done in the last few years and put that inside. Also look at how other ecosystem drivers such as temperature and salinity could actually affect what's happening in our system. And so for this, we also got the management on board, which is, they should have a word to say. And so the idea was to say, are the models that we're using representing what they need, which is reef-scale intervention. And so what we did is, we went a bit overboard, I have to admit. We went with 3 different hydrodynamical models. These 3 models have been validated, have been for the Great Barrier Reef. They've been used, they've been published. And what actually varies with them is there's a lot about the resolution, but there's also about the way that they're representing. So some are depth average, some are 3-dimensional, some just do the barotropic, some also include the baroclinicity. So these 3 models were then, so one is actually run by ERIF, but they were run for the periods where we needed to understand COTS dispersal. And we varied the frequency of release to capture as much of the variability that you have during the summer season, which is due to the monsoon trough just wandering around and being also driven by climate drivers such as ENSO. And we also varied the egg buoyancy, so we actually the biologists told us, well, you should actually test this. So we've run a range of tests. And then we've also updated the post-processing, same with the biologist. And so all of this ended up being that result. I know I shouldn't have presented it, thank you very much. But that's pretty much kind of I know. So 5 minutes, thank you. So yeah, that is kind of a summary pictures of what we've produced over all of these. And the idea is they are kind of similar. That's the connectivity matrix. So source to sink. I added the latitude on it because I like it. And it was just to show you that there's variability, but there's a lot of agreement between the model as well. And so the first one is slim, so it goes down to 250 around the reef. The second one and third one are actually the same model, but we've used different tests, so moving the particles so they could actually go at different depths depending on their age. And the third one is run by ERIF as well, so it's using GBR1. And so the idea was, actually, do we see any agreement at reef scale? And I think this picture is actually representing what is going inside the reef prioritization. So they're using network properties, these 3, for example, so out component, total node strength, and the node out degree. And so each of the colors represent the model comparison 1-to-1. And what you can see is there's not that much agreement at reef scale. However, if we step back and we look at this matrix and we say, okay, so maybe we don't have that much agreement at reef scale, but if we start looking at what reefs are actually really connected to each other, can we actually find a different way of looking at the reef that could be maybe more beneficial for management? And that's what we found. Like if you actually, it's a simple cluster algorithm, but it looks at the connections between the reef. And what we found is actually the 3 models at the surface tend to agree pretty well. So they find the boundaries are quite similar from one model to the other. So that could be a different way of adapting management to dispersal model output. And however, what we found also is it's very sensitive to the biology. Therefore, you just change a little bit, which was instead of having the dispersal being kept at the surface, we actually let them go deeper, which was what the biologists told us could happen. And then you end up with different communities. And so I think it kind of shows that biology is extremely important to dispersal. So what we've learned is we're probably not resolving with this regional scale model the reef scale. But we may actually be onto something into understanding better how groups of reef are actually connected. The gaps in the COTS larval biology is something, and I think we're mentioning COTS here, but I think it is true to anything that lives and use pelagic larval life at one point of their life on the GBR, means that yes, there's still a lot of work to be done. And so moving forward in a very highly variable environment, we should probably go towards a higher resolution in hydrodynamic. So I think that's one point that is going to be mentioned again in the next two talks, that this is needed. Larval biology is also something that we're going to have to spend more time and money on. And we actually, all of these results are already used as input into the reef prioritization. Well, thank you very much. That's everybody that has had an input in this project. It has been great to work with all of you. And that's it. I've just left that as this is the output for the project.
Thank you, Severine. We have just 2 minutes for questions, so I might take one quick question from the audience. If a quick question is possible, Chris.
Thanks. The clustering, is it based on sink or based on source? I just wonder if, like, how did you cluster? And is there, like, genetic study that would confirm what you found in terms of, like, clustering?
It is based on the dispersal strength between reefs. So it's not just source and sink, is how well connected you are to your neighbors. The genetic, I think, well, talking to the LTMP, they love that community, not for the COTS, but it kind of talks to them because it's like, well, actually, we can relate some of the community that you've been observing to this. It'd be better to do it for fish, and we've got the data, so we should run it. But yeah, genetic is something that is hard to come across in the GBR, but we've had the chance, and there's few of us here that have actually used parentage analysis in other places. And yes, it would be great to have more validation. It would be, yeah. We're up, like, if you get genetic data, we would love that. Thank you.
Okay, thank you, everyone. Our next speaker is Robert Mason from CSIRO. Thanks, Robert.
Okay, thanks everyone for joining me for this talk. So this talk is about validation of coral larval connectivity models that has been done over the last 3 years with the collaboration of researchers from different fields at CSIRO. So just to recap, so reef connectivity, what are we talking about? We're referring to the origins and destinations of coral dispersal. That's the demographic links between reefs. So I'm more focused on the demographic flows that contribute to reef recovery as opposed to connectivity that on an evolutionary timescale, which might be much smaller in a demographic sense. So connectivity in a demographic sense is relevant, of course, for reef restoration because demographic links may help supply a degraded reef with a source of new recruits that will assist in that reef's recovery. So just as an example of this, in the 2016 and 2017 bleaching event, we know a great deal of the northern and central reef bleached. And as an exercise, I and colleagues performed a connectivity spatial analysis of where the key reefs for recovery for those reefs that were damaged during this event would be. So we searched for, using our connectivity matrix, we looked for reefs that weren't damaged during those bleaching events and that were very strongly linked in a connectivity sense to reefs that were damaged. And those reefs in blue in the diagram on the right are those identified reefs. So this is an example, although a past example, of how connectivity is important in a reef restoration and management sense. So in terms of a study in connectivity itself, because of the huge spatial scales that we're talking about, we really can only do it using modeling and simulation. So typically what's done is we generate a hydrodynamic model, and then using that model, we engage in a Lagrangian, typically particle tracking step. And we track the locations that particles released from a number of reefs, or all of the reefs that we're interested in that particular environment network travel to. And then using those particle trajectories and endpoints, we then generate a connectivity matrix from all that data. So that's the typical process that's done on the Great Barrier Reef and in a great number of other marine ecosystems around the world. So the purpose of this whole study was to validate that simulation process. And what we did was 2 experiments. The first one was done in the Capricorn Bunker Group. And we used a model that was focused mainly on the islands and the reefs in that group. It was a 300-meter resolution model, and it was performed in a CSIRO's shock modeling framework. And for the validation experiment itself, we focused our fieldwork on Wistari, Heron, and Sykes reefs in the middle of the Capricorn Bunker Group. Our second experiment we did in the Palm Islands, and we had a model that covered a much larger area. It covered most of the Central Great Barrier Reef. And for our fieldwork and experimental work, we went to the Palm Islands. And this was facilitated by a different hydrodynamic model. It was an unstructured grid, and it had 100-meter resolution around the Palm Islands, and then 1 kilometer resolution elsewhere in the Central Great Barrier Reef. So our methods, this is a summary of the methods for both sites. What we did, we first of all, sorry, I'll go back. We chose 10 to 12 sampling stations around the reefs in our target area. And then before spawning, just before spawning occurred, we would go to those sampling stations and install settlement tiles, so 15 tiles per sampling station. Then once spawning has occurred, we then visited each sampling station every day and performed plankton tows, and then sorted those tows and counted the number of coral larvae within. And so following a period of approximately 2 weeks, we then went back and retrieved the settlement tiles and counted the number of coral spat that had settled. So we have 2 sources of information here for that we're using to validate connectivity. We have coral larval densities in the water column and spat settlement. So this is an example of what the data looked like for the Capricorn bunkers in our very first spawning event there. So we have, in the blue lines, we have the time series of coral larval arrival. So that's the density of coral larvae in the water column over time following the spawning event. And then the graphs there show the cumulative settlement of spat over that period that the larval or the plankton toes were performed. So there's a lot of, a fairly rich data source here, and there are spatial patterns that I won't necessarily go into, but there's a lot of good information to explore in the future there. We also went back to the Capricorn bunkers in December 2022 and got information on spat settlement at those 12 sites and on larval arrival over the post-spawning period. And when we put all this data together with our model predictions, and I should just make the point here that we set up the model to predict spat settlement and larval arrival in two different ways. So, thanks. So the spat settlement was predicted by applying competency and mortality relationships. So larvae that were both competent to settle and that were still alive. And whereas our larval arrival was just based on applying mortality. So what we found when we compared our modeled and measured values was no significant relationship between larval arrival and larval arrival predictions. So that's on the left. Whereas when we looked at spat settlement, our model was able to predict with significance spat settlement around those 12 stations and across 3 spawning events. However, there was a lot of variance there. There's a fairly low R-squared value of 0.12. So next, going to the Palm Islands, we implemented a very similar sampling scheme and have a fairly similar format of data there. And looking at the model predictions versus the field measurements, for larval arrival, again, we didn't have a significant relationship between the model and the measured values. For spat settlement over 2 spawning events, we did find a significant relationship with an R-squared of slightly better at that time of 0.19. So overall, these 2 different models are successful at predicting realized connectivity. That is, the larvae that arrive and that settle at reefs. However, they both failed at predicting larval arrival itself. That could be because we had fewer data points. Logistical constraints prevented us from performing the plankton toes for as many time points as we had spat settlement data for. It also could be because of the inherent stochasticity of planktonic sampling, and that may have generated more variance than our sample sizes could cope with. So yeah, both models were able to successfully predict, although with a great deal of variance, spat settlement or realized connectivity. And this is really good news. The challenge now is to go back and identify the factors that are important in building models that can predict realized connectivity, so that these models can be built for other areas or for larger areas for operationalized restoration. So I'll just end there with thanking everyone who was involved in the field work and behind the scenes work. So it took an enormous number of people or person hours to do the field sampling, tile scoring, plankton toe sorting, and also contribute to the modeling behind the scenes. So thanks everyone for listening.
Thank you, Robert. Great to see a talk with plankton sampling involved, always fun. Questions for Robert? No, thanks, Barbara.
Robert, very good talk, thank you. And good to see some actual data coming into the validation. Now, this is an unfair question, but it's seeing how, even quite a detailed, carefully built hydrodynamic and particle tracking model gives, at best, fairly low squareds, and that this connectivity is one of several inputs that goes into the ecological outcome models. Would we be better off, rather than trying to get further and further into getting the connectivity right, applying some simple heuristic around the distance between source and sink sites and leaving it at that and putting more effort into reducing other sources of uncertainty?
Oh, so that's my stop timer. I think that's a question for maybe in a more in-depth analysis. I guess, how the uncertainty that we see in these models, as shown here, how that might then propagate into how good a decision we can make using this data, as well as all the other data that's involved in modelling on decision support. That is probably an analysis in itself. So maybe the answer is that simple heuristics are better. I wouldn't want to say that they are yet without doing that analysis or propagating that uncertainty in a formalized framework, doing the tests to show if that is problematic in having good decisions at the end of the pipeline.
Yeah, another difficult question, but I just wondered, in terms of the challenge of making predictions in the space, I wonder how much of the uncertainties around what happens right near settlement, as in you've got a limited resolution there, and of course that once you're over the reef and there's all the issues about retention and so on, I wonder whether that's a real, a strong driver of the errors that you might be seeing.
I would concur with that as being a probable source of a lot of the variance that is being seen here there. There's the filters that you might have, like the very fine scale currents, that might particularly affect whether some or many coral species larvae can actually or want to settle in those locations. So yeah, that very fine scale hydrodynamic filter is certainly not represented, and whether it has a large impact in the end or not, I guess that's perhaps still an open question, but it would be a sensible hypothesis that those localized factors and perhaps also biological factors such as community assemblage at those sites, they would be, in my mind, likely candidates for generating very localized, strong filters on settlement.
Thank you so much, Robert. Robert did a good job with some difficult questions. Next speaker is Clothilde Langlais. Thank you, Clothilde.
Thank you. So we're going to keep going into hydrodynamics and models, but I think I'm going to even step back a bit. So I would like to talk to you about all the different hydrodynamic scale of the marine dispersal, and also emphasize the strengths of those models, but the weaknesses and the limitation that we really need to keep in mind. And I'm going to use the example of those 3 projects listed at the bottom, so some from ERIF and a couple from the Reef Restoration and Adaptation Program. Here we go. So I guess we already heard about that a fair bit during this session, but marine dispersal is very important to support coral restoration, and that's because we've got those marine species that their reproduction rely on this dispersal of coral larvae. And on this figure is just a photo from Ames showing some coral spawning slick that are at the surface of the ocean, and their displacement is really due to the ocean circulation. And then those coral larvae are going to be dispersed and move around and maybe reach other reefs. And downstream, we often use that for those reef connection, and we try to identify which reef is going to be, a receiving reef, and some others that's going to be the source for others. And that's where the decision I made downstream. And sometimes those connections can be big, up to hundreds of kilometers. And here that's just an example showing how the Palm Island is connected to other reef in the central GBR. But like I said, I'd like to step back a bit and talk about the marine dispersal and how we give you the best estimate possible of that. And there are those 4 steps I like to talk about. And the first one, again, is this hydrodynamical model that Sev talked about, and then Rob presented as well. Then we go into the Lagrangian tracking and the biophysical properties of those tracks, and then we go to the connectivity. In all of those steps, there are strengths and weaknesses along the way. But today I'd like to go back to this first step, those hydrodynamical models. What can they do? What are the limitations? Because this is very important to not forget when you go all the way to decision making in the end. So in my mind, there's 2 different big scales in the Great Barrier Reef. The first one is the GBR wine. We want to look at the old World Heritage Area. We want to understand the inter-reef connection through those 2,000 kilometers. At that scale, we actually know a fair bit of what the circulation looks like. We've got the South Equatorial Current coming in, we've got the shelf break current, we've got area of upwelling, we've got a lot of tidal circulation inside the lagoon, and some wind-induced current. So we sort of know the physical processes that are happening. But there's another scale that is very important for restoration, and that's the scale of the reef. And in there, there's sort of 2 subscales. That the fact that we want to understand the connection between the reef, and that's sort of the bottom right schematic there, that look at the connection between reef. But we also want to understand what's happening within a reef. So the self-retention and the connection within a reef. Is there area where there's high supply of larvae and others where there's low supply of larvae? So there's and those ones like are hundreds of meters to kilometers. So there's this, big variety of scale that we want to resolve. And for this very fine scale, that's sort of the band at the top of the schematic there, we can see those little recirculation at the back of the reef, those little vertices and eddies. That's the one we want to reproduce with our model if we want to be able to model and reproduce self-retention. So I'm going to give you an example of those different scales across the different projects I've been involved in and the different model we use to try to represent those scales. So the first one is the ERIF model. And that's when you want to understand the connection and the connectivity throughout the whole Great Barrier Reef. And through ERIF, we've got 2 types of model, the 4-kilometer one and the 1-kilometer one. And that's an example on the right of the circulation we get with the 4K model. With that resolution, we can see the shelf break current, we can see the upwelling area, so the color is the temperature, and we can see the tidal movement. And some people in the community, some people are using the 1K or the 4K to do downstream product. It's important to remember what are the strengths and limitations of those models. So both of them, they're very good at representing this large-scale circulation. So there's going to be good advection and potentially inter-reef connection. But at the scale of the reef, with a 4K resolution, or even a 1K, you cannot reproduce the local retention or the within-reef connection. It's not possible. It's just the size of the model cannot do that. You won't be able to represent the flow between the channel in a reef, unless your channel is 8 kilometers wide. right? It's just not possible. So we need to think about that when you use those product downstream. Then I'm going to go into some example of those very fine scale resolution physical processes we really want to reproduce when we talk about those high resolution model. And then again here to remember, the key is the bathymetry. It's not that the model is missing something. It's just represent whatever it can represent with what we got at 4 kilometers. It's not a lot of reef. So let's go to the high resolution model. And the first example here is the cap bunker that Rob just presented before. And we've got, it's going to move, it is. So we've got temperature in the middle and salinity on the right. At those scale, you can see what the circulation is doing. So we can see sometimes the effect of the wind when there's a very strong blowing, but we also can see the tide turning around. Now, if you start to look in between the reef, you can see how the tidal current is channeled very strongly in between those reefs. What you can see as well on those plots, and you can see inside some of the lagoon reef, the semi-enclosed lagoon, the temperature and the salinity show a different value than outside of the lagoon. It means that the model can represent this semi-enclosed lagoon behavior quite well. We can see as well at the wake of those reefs, sometimes there's some little vertices that start to appear. That's the fine scale little eddies that you really want to represent at that scale. And that's just a quick validation. So we had an ADCP south of Heron Island or Heron Reef, and that's how well the model represents the circulation over there. So we've got the tidal movement, that's the back and forward, but we also have a kind of modulation of that signal, and that's sort of the large-scale circulation that is happening over there. So the model was doing quite a good job at representing that large-scale circulation. Then there's the Palm Island model that Rob also introduced. Here we're also looking at, fine-scale channel, and this animation, I want you to look at is this current that are pushed through in between the island. They are pushed back and forward by the tide. And what's happening, you can see a lot of little vertices spinning off. And on the left here is just a still image of those vertices. So that's in between the top of the main island, so the channel on top of Palm Island. And you can see the scale of those vertices. They grow and they go to 2 to 3 kilometers. And that's the one that's going to converge your particle, going to converge your larvae, and impact the local supply in this area. So that's what the model can represent here. Now the last model is the Lizard Island model that you might have heard about in the next talk coming up. There we went very, very high resolution, 50 meters. Is it going to move? It's moving too, great. For this one, again, you can see on the animation that's temperature and current. We can see the tide going around, but there's a bit stronger influence of the large-scale circulation at the size of the island. Now you can look inside the lagoon in the south, and you can see how the tide coming in and out of this lagoon, but also there's some period of very calm current when the current is very still. So that those slack conditions that when you do those moving coral and restoration program, you are looking for those very calm conditions, and so people in the field can deliver their competent larvae. And that sort of, those calm conditions is what we are trying this model to reproduce as well as possible. On the right is sort of a zoom in the south in between the two islands, just to show how resolution the channel are, but also to give you a comparison of how good the model is doing. So on the right, you've got the current direction. So again, it's quite bipolar. It's because of the tide coming in and out. And you've got the variability, the time series of the current, more on the left or middle, and you see how well the model fits at those spots anyway. Just to zoom in again in that channel is to show you how dynamic that is. And that's at 2 meter deep here. Because it's very shallow, at 2 meter deep, you've got just a channel in there. And you can see how the flow is rushing in and out. And there's some very strong acceleration and a lot of change, and that's a very viable environment. And so that's the challenge here. That's what we're trying to model, and that we're hoping represents the reality. So in sort of conclusion for those small scale, there's all those things those models can do really well. So they can sort of do really well inter-reef connection. They can represent those fine-scale processes, those convergence zones, and a bit of retention. And they can sort of represent within reef pattern. And that's sort of summarized there in one of the figures from Robert around Aran Island. Those are the modeling result here. And you can see those pattern of connectivity around the main reef. They're actually reproduced from one year to another. And the sort of high connectivity area are the same across all those spawning events. And that's what the hydrodynamic is doing. But those patterns, they're not at the scale of 100 meters. There's more at the scale of 1 kilometer. And that's sort of what the model can do, is sort of represent those patterns at 1 kilometer, not at 10 meter or 50 meter. That's too big of an ask for the model. Now we need to think about the limitation as well, and there's quite a lot, and we shouldn't shy away from that. And there's a few examples from the analysis that Marine did in Lizard Island. And some of them, that small bay, in the north of the island, there's a small bay called Mermaid Bay, and the model didn't work really well over there. The bay was too small, not enough grid point in there. It didn't work. And the bottom of the model is the same everywhere, when in reality you go out in a reef, there's some sand, there's some rock, there's some reef, so the friction at the bottom can be different. And here there's an example where our tidal model is completely out of phase. And it's just because the tide was not slowed down in the model world. Now just to conclude, we've got those two scales that we're using, and that's the best estimate from, I guess, modelers trying to give our product out there. They're the GBA wide scale and they're the very high resolution scale. There's limitation in both worlds, but at the moment, those both worlds are split. And ideally, we would like those two scales to converge in the future, so we have one product that can resolve all those scales, the large one and the small one. And that's sort of where I'm getting at just with that last slide, and that we're sort of trying to work toward that in the modeling world, in the hydrodynamic model world, where we'll have unstructured model in 3D covering the whole GBR, and we have very fine scale resolution across the reef matrix and lower in the coral sea. And that's what it could look like in a few years when we're able to run those models on long time scale very efficiently. But that gives, a beautiful picture of the reef with a shell break current, the upwelling at very fine scale, and all the little channel and current going there. Thank you.
Thank you, Clothilde. I could watch those little simulations for hours, but in the interest of time, we've got time for one quick question. Okay, join me in thanking Clothilde. Thank you. Right, so our final talk today is actually two short video presentations. So I think we're playing them in succession with us. There'll be a small switch over a video in between. George Roff is one of the speakers. I've seen Jez around, so he might be here to answer questions. No, he's not. Oh, Chris, sorry. Chris will be answering questions at the end. Thanks, Chris. So let's enjoy the pre-recorded videos.
Good morning. Apologies, I have the flu and therefore I couldn't present in person in Cairns. So I really hope this recording will work. George and I will present some of the work we have been doing to predict the dispersal of coral larvae in the context of coral larval restoration, which is led by Professor Peter Harrison and Dr. Christopher Doropoulos in the Moving Coral sub-program within RRAP. I am a postdoc researcher at Southern Cross Uni, and George is a senior experimental scientist at CSIRO. Moving corals interventions are all field-based that take place during major spawning events, when buoyant coral gametes rise up to the surface and form slick, which we target and collect, and then transfer into rearing ponds. In those rearing ponds, we let larvae develop until reaching competency. Once larvae are competent, we then transfer them using various methods onto the reef to kickstart their early recovery. So as our operation occurs on the reef, the intervention are subjected to local environmental conditions, and the one that has the most influence for us is the current. So as you know, ocean waters are constantly in the move. They, especially at the surface, we call them surface current. They occur in the top 50 to 100 meters of the water column. So these currents are usually set by the wind that drags the surface of the water into one direction and then create flows. But there are also interacting factors playing here, such as the Earth Coriolis effect, the shape of the seafloor, tides, river inflows, wave, and local weather conditions. And from studies measuring currents on coral reef, we know that, for example, current speed can vary up to 15-folds among coral reef habitats. So luckily, there has been lots of effort over many decades into modeling hydrodynamic environment in various habitats and at various scale. And we are making use of this accumulated knowledge to test fine-scale biophysical model and its ability to predict coral larval dispersal during restoration intervention. So here you can see the different models that we have trialed and tested over the past few years. So the first one was in 21 and 22 called the LIS model, which has a donut shape and a domain of 8 by 8 kilometers with a fine resolution close to the reef that increases as you move offshore. This model has a nested regular grid of about 50 meters to allow for particle tracking. And it was integrated with Condie. Then in 2003, we upgraded to an unstructured grid that basically looks like a honeycomb, as you can see on that photo. So the domain is approximately the same size, 8 by 8 kilometers, and we tested two different models, one around lizard and one around airy reef. With this modeling workflow, the particle tracking component is embedded within the modeling suite as form as plugins that were developed by Jack Beardsley from CSIRO. That basically allows automated processing, which become really useful when we are in the field. So these models are three-dimensional. They operate at a 10 to 12 minute time steps. They do have 30 meters resolution near reefs, and they provide a forecast hydrodynamic condition and associated particle dispersal output up to 6 days ahead. So having this forecasted condition is very useful during fieldwork to predict spawn slicks convergence zone. So here you can see on the left, we have forecasted hydrodynamic condition during spawning nights last year. And on the right, we have the relative reproductive output of reefs around lizard. Here we used coral cover, reef area, and the relationship between cover and spawn produced on reef. We then integrate this information into the particle tracking component of the model to model spawn slicks. So we get a forecast of particle concentration during predicted spawning nights, and we can identify what we call convergence zones of coral spawn slicks, which is where high concentration of coral spawn will likely form. So this helps us make decisions on where to go what we call hunting for spawn at night, for example, but also where to deploy spawn catchers a few days before a likely spawning event. So here you can see the forecast of particle concentration around lizards throughout one of the spawning nights at 10 p.m. midnight and 4 a.m. the next day. The model also assists us in predicting dispersal during delivery of coral larvae on reef. So when larvae in the larval pools are competent to settle, we then transfer them onto damaged reef. And we often have only a 5 days time window to do that. And during these 5 days, hydrodynamic condition can be very variable because of the current, the wind, the tide, and so on. So we use the model to forecast the dispersal of larvae during 12 to 24 hours following delivery, hourly from 6 a.m. to 6 p.m. for 5 to 6 days. And the goals of this simulation are first to identify location, day, and time of the day where local retention is highest to maximize local settlement of a damaged reef, and second, to predict the footprint of larval releases. This is an example of some of the findings from the modeling exercise we did. So we dispersed a set number of particles at 25 reefs in the southwest region of Lizard Island during delivery condition in 21 and 22. And we calculated the residence time of particle within 1 hectare of the delivery location. So overall, we found that out of these 25 sites, 20 sites had one or more occurrence of particle residence times over 5 hours. And some sites show residence time of 12 hours quite frequently. So these sites therefore make ideal candidates for larval releases from a hydrodynamic point of view, of course. Through this exercise, we also found that slack current condition, which is the time periods on the reef where the current is quite weak and could lead to high retention of larvae, are completely unrelated to the timing of high and low tide, and therefore tide is a very poor indicator on when to release larvae on reef if we want to maximize their retention. So overall, during free releases of larvae on reef, the timing of larval delivery is key, and the model can assist us in predicting this.
So as Maria's outlined in the previous section here, in terms of upscaling larval restoration, the hydrodynamic models have been able to provide insight into one of the key questions of larval reseeding, which is where do larvae disperse following release? So from the tens of millions of larvae released onto damaged reefs during free releases, how many settle in the immediate area, and what are the spillover effects into adjacent habitats? And the next logical question from this is, where do the larvae settle following release? So, and this is important in terms of converting the number of larvae into expected densities in terms of a production rate, but ultimately we're looking to quantify the spatial footprint of larval restoration. To quantify this, we developed coral-COTS, which is a spatial explicit probabilistic model of larval settlement that leverages these high-resolution dispersal models. So coral-COTS is an individual-based model, allows upscaling from small-scale simulations of thousands of larvae to large-scale simulation modeling of releases of tens of millions of larvae. Coral-COTS is spatially explicit in terms of incorporating these larval particle tracks, but also interactions with habitat maps. So where are larvae passing through space and time, and are they passing over habitat that could be suitable for coral settlement? So it's also adopts a Bayesian framework, so it's probabilistic in terms of determining settlement outcomes, and importantly, it's parameterized on experimental and field data generated under the RRAP components. So to give an example as to how coral-COTS works, here's a trial run from Pedro Reef at Lizard Island, and this is based on simulations we ran back in 2022 during the mac coral spawning in December. So in contrast to 2022, here's what Pedro Reef looked like a few weeks ago, March 19th in 2024, showing more than 90% of the corals were bleached and the onset of mortality in these corals following prolonged thermal stress. And this is a reality that faces many of the reefs on the GBR today. And upscaling restoration efforts need large-scale responses in order to be able to mitigate some of this damage moving forwards. So this little box in the top left of the map here is our release site on our restoration hectare, and we're simulating 1,000 release particles from this release box. So these are the larval dispersal paths. This rainbow color shows the dispersal from 0 to 12 hours following release. So when larvae settle following release is a challenging question, and it's key to understanding larval reseeding approaches. So to better understand this, we conducted a series of experiments, both at CSIM and during coral spawning at Lizard Island, to parameterize this time to settlement model. And this is a Bayesian modeling approach that determines the probability of each larvae becoming competent, and then maps the competency to these simulated dispersal pathways to determine when and where larvae are in space and time when they become competent to settle. So the spatial component of the model is then enhanced by using the Allen coral atlas layers to determine the seascape configurations of different habitats for reef back reef and reef slope. And then based upon larval activity experiments, each of these different habitats has a different probability of settlement for coral larvae based upon larval preferences. So we then take these habitat maps and turn them into a mosaic of settlement probability, which allows us to generate seascape mosaics of settlement probability, where in this map, the darker colors represent a higher probability of settlement on the reef. So combining probability here, we can then determine the potential spatial locations of larvae that settled on the reef, and then the proportion of larvae that were diluted and lost to off-reef dispersal. So focusing in here on the fine-scale settlement patterns on the south of Porphyry Island, you can see these grey dispersal tracks and then the final settlement locations of the larvae in the dots below. And one of the benefits of these spatially explicit models is that we can then quantify not only the total numbers of larvae settled, but also the underlying spatial patterns such as settlement density, but also the spatial footprint of settlement, which allows us to evaluate the impact and the scale of these receding programs for the first time. So in summary, the coral sea model aims to provide insight into key knowledge gaps in larval restoration. Where do larvae settle following release onto reefs? And what is the spatial footprint from larval reseeding projects? What can be attributed to settlement in the area we're looking to restore? And what are the benefits from spillovers into adjacent habitats? What are the likely densities of settled corals we can expect when restoring damaged reefs? And then what densities of adult colonies are produced from reseeding and where are they located? So an additional thing we've been looking at doing with coral seed is how do we vary the initial model parameters, and can we really test the ecological limits of larval reseeding? So to what extent can larval reseeding scale towards large-scale restoration? How do we take these small-scale efforts and look to restore damaged reefs, such as entire reef flanks, kilometers in length? And importantly, we've been looking to see whether additional interventions can improve on investment and return as part of the larval reseeding. So Marine's already introduced an example of this in terms of optimizing releases to coincide with slack tide periods. But we've also been looking to see how we can enhance larval retention through the use of bubble curtains to entrap larvae or acting as barriers to restrict dispersal, which in turn enhances settlement, or how incubating larvae with inducers such as coralline algae prior to release may reduce competency times and accelerate the settlement onto damaged substrates. And finally, we've been exploring how time-delayed releases can improve settlement densities by releasing larvae when they're competent to settle, and that has an immediate impact on settlement following release, as opposed to delayed dispersal. So in summary, Coral Seed is written in R and is open source and will be available for anyone to use. And importantly, the model is flexible in terms of parameterization and works with a diverse range of dispersal models. The code is available on GitHub, and a manuscript on the underlying theory and the applications of the Coral Seed model is currently in draft form. And with that, on behalf of Marin and I, we'd like to thank CSIRO and SCU, as well as the RRAP for funding model development and fieldwork as part of the Moving Corals program. And special acknowledgements to Lizard Island Research Station and the staff at CSIMS for accommodating our experimental and field-based research.
I had one. I thought so in Marine's presentation, so what she mentioned, that was a mismatch between the tide and where the larvae ended up. Was that the case?
The mismatch that Marine referred to was a mismatch. As field ecologists, we often think that at the high or the low tide periods, the slack tide periods is actually when you get low current velocities. But because of the dynamic nature of coral reefs, that would probably work in the open ocean, but that doesn't work on a coral reef consistently. So some parts of the reef might match up with the slack tidal periods, but other parts don't match up as well. Yeah, Clothilde, maybe you can add to that or correct anything that I did incorrectly. Yep.
Okay, any further questions? Okay, thank you, Chris.
Oh, thank you.
Thank you everyone for attending this morning. It's now a break for lunch, but we'll reconvene at 1 p.m. sharp. Okay, don't be late.
To the decision support tools and models session. It was a last-minute change, so I'm sharing this one. For this one, for the first talk, we're going to have Barbara Robson, and we're going to have, again, 12 minutes, and I'm going to give an announcement of 2 minutes, just closer to the end. So we give time for presentation. Thank you, Barbara.
Thank you, Manu. And I'd like to acknowledge first that this is a product of a group effort of the Model Evaluation Working Group of the RRAP Modelling and Decision Support Ops team. So we've heard a lot about models already in this session. They're being developed to inform both operational decisions when we're out there and deciding where to go to, release some of our interventions, and longer term strategic decisions about what interventions we can make to support the Great Barrier Reef and its resilience. But we're really working in a fairly uncharted space. We're talking about interventions that we haven't tried before, that we're just developing now. And we're talking about fairly long timeframes. So within the RRAP modelling and decision support space, we're developing a range of different models and decision support tools associated with those models that are designed to operate on different scales and in different contexts, but collectively to give us a better understanding of the potential implications of the actions that we can take now to support the resilience of the reef. But how can we know whether our models are really fit for purpose, whether they're going to be helpful in making the right decisions in the years to come and right now? And I'd like to propose that if a model's fit for purpose, it needs to be sufficiently accurate. It needs to be sufficiently informative for the decisions that are being made or the other uses to which it's been put. It needs to be sufficiently transparent. It needs to be trusted by the people who will be making the decisions and by the people who will be most affected by those decisions. And to some degree, that's an outcome of it being accurate, informative and transparent, but it also depends on the appropriate relationships and conversations having happened. And finally, to be fit for purpose, the model needs to meet the operational requirements of the context in which it's being used. So I'm just going to talk a bit more about each of these considerations. So what does it mean for it to be accurate? Well, again, when we're working in an unknown space, projecting into environmental circumstances, which are going to be quite different from what we've had in the past, we need to know that the models capture what we do know about the reef as a system, and it isn't enough to simply fit the past observations, both because past observations are fairly sparse when we're talking about a system as big and hard to measure as the Great Barrier Reef, with so many different factors that we're interested in preserving, and because things are changing and the environmental conditions of the past are not likely to be those of the future. And so when we're dealing with using simulation models to project out into change conditions, there's a framework that we'll be adopting for evaluating the accuracy of models, which is called the 4-level or the concept state process system framework. And in this framework, the first level is conceptual evaluation. So that means a few things. It means, does the model pass that aft test? Does it behave in ways that correspond with what you know about the system? Does it embody what you understand about how it works? And does the code actually do what it says on the box? Second level is state evaluation, which is are you matching past observations of the state of the system, such as coral cover time series. Third level is going a bit beyond that into process evaluation, which is looking more at rates of change, and is your model correctly predicting, for example, how quickly a reef recovers after a bleaching event. And the fourth level, which can really help, especially if your observations are relatively sparse, can help you to believe or check whether the models are able to predict the right things for the right reasons, is the system level evaluation, where you're looking at system properties that emerge that are not built into the model, but may emerge from the complex dynamics of the system. And they may be things like the distribution of different types of communities from inshore to offshore, or from north to south, or the ratio between juvenile and adult corals at a given time. So we've done some brainstorming within the group about the different sorts of metrics that we might use under each of those four levels. And I've just put one example for each metric there, again, to give you a better idea of how the models that are being developed within RRAP might be evaluated before we use them to make decisions. And we've also looked at what data sources are available to us to do these evaluations. So that includes things like the long-term monitoring program and marine monitoring program, mantitos and other observations, photo transects, eco-RRAPs, in situ observations of things like coral responses and community, and as well as hydrodynamic observations. Robert's larval tracer experiments, which you talked about before lunch. Some of the experiments looking at responses that have been happening in CSIM, as well as potentially in future we may be drawing in some of the DNA monitoring observations. Second, so on that accuracy, we can set targets for exactly, what metrics, what R squared needs to be for it to be useful enough, how much bias we can have between the model and the observations, and that sort of thing. But then we need to go on to the second part of fitness for purpose, which is that the model is sufficiently informative. And that means it's providing the sort of information on the right sort of scales for the decisions that you're going to be making. And because I've got a limited time, I won't go more into that now. The third component is that the model is sufficiently transparent. That covers a range of things, only a few of which I've put here, but that's about can the modelers explain to the people that need to understand it how the model works? Has its behaviour been tested so that we understand how well it works and what unusual outcomes it might produce? Has it been thoroughly documented? Has the code been made available? Have we documented how strong the evidence base is behind the assumptions that we build into the model? Have we documented what those assumptions are and where they might not work? Have we been clear about how much uncertainty there is in the predictions and so forth? And within RRAP modelling and decision support, we're taking a number of steps to make sure all our input and output data and our model code and so forth are documented and available, and the workflows that we use will be documented so it doesn't just rely on the particular people who built the models being available to do every run. Fourth, as I said at the start, the model needs to be trusted, and to some extent making sure it's well documented, that it's peer reviewed and so forth will build that trust. We also need to be having conversations, having discussions about the modelling with the people who will be using it and be affected by it, presenting in forums like this. We need to make sure that it's not a one-way thing, that we understand the needs of those stakeholders and understand what it will take to earn their trust. And finally, the models need to meet the operational requirements of the context in which they'll be used. Now, I have a AI-generated image here. Here we have a clock. It's probably quite accurate. We can understand if we spend a bit of time reading up on clockwork, how it works. So it's probably reasonably transparent. It probably gives us information we need. For instance, it'll give me the information that I have less than 2 minutes left to talk. And so Manu will know when he has to kick me off the stage. But it doesn't meet that operational aspect of fitness for purpose. It's a bit clunky. It's not something you're really going to wear on your wrist, and it's going to be quite awkward. It's not fit for the purpose of being a wristwatch. So for our models, we need to assess operational requirements, like can it run fast enough to inform a decision when a decision point comes up. Some of the models we're using take weeks to run. But that's okay for some sorts of decisions and not others. Is it robust and reliable to run when we need to run it? Or might we expect to have to do a lot of, stops and starts, to actually get it working each time we need to run it? And what does it take to run a new model for a new scenario? Is there a lot of development work and data sourcing each time, or is a lot of the process relatively automated? Do we need the particular person who developed it to press the button and run it? Or is that a workflow that can be handed over to someone else if they're on holiday or if they've moved on to another project? And they're the sort of things that are part of the design considerations for these models and that we need to get right. So just the summary again, if I haven't run over time already. We're aiming with these decision support models to have models that are sufficiently accurate, sufficiently informative, sufficiently transparent, that they can be trusted, and that are operationally suitable for the range of decisions that they'll be used to inform. And yeah, just finally, a list of names of some of the people that have contributed to these discussions.
Any questions for Barbara? And may I remind you that we need to use the microphones for those online. Any questions online?
Thank you, Barbara, for a very interesting talk. I'm just wondering, do you have any examples that you evaluated using this principle?
We haven't actually applied this to our models yet, but we've set up the framework that we will be using. So no, I can talk in more detail. We've been thinking about this evaluation as we continue to develop the models. So, for instance, we know currently that some of our models aren't yet meeting the operational requirements. There's too much of a scramble, and they're a bit slow if we're given a decision that we need to inform. And so, with this in mind, we're working on making those workflows smoother and making the models more robust and so forth. But I don't have a full work through for any of our models that I can show you at this point. Although, if you're interested in the accuracy part of it, I did publish a paper a few years ago applying that 4-level framework to the e-reefs models, particularly the water quality side of it. So I'm happy to share that with you.
Thank you, Barbara. Thank you. And next we have Cameron Fletcher. Hi, Cameron.
Hi everyone. I'd like to start by acknowledging the traditional owners of the country that we're meeting on today and of the Great Barrier Reef and its catchments, and pay my respects to their elders past, present and emerging. I'm Cameron Fletcher and I lead the response sub-program of the COTS Control Innovation Program. And one of the bodies of work that I coordinate relates to research designed to help managers and on-water crews in the COTS Control Program make ecologically informed decisions more effectively. These include decisions like where around a reef to drop cull divers, when to invest in monitoring and when to change management strategy based on the data that they're collecting. Today I'm going to tell you about the next generation decision support platform that myself and a group of researchers across multiple organisations, including JCU, CSIRO and Gurumpa, have developed as part of the COTS Control Innovation Program. The platform integrates multiple components: an information system to coordinate and share data, automated digital workflows to process that data, empirical analyses to adaptively update key control program parameters, and decision support tools that put the outputs of these efforts right on the screen in front of decision makers at Gurumpa and on water at the moment they're trying to make those decisions. This is tied into a number of projects within the COTS Control Innovation Program and also the ongoing innovation in the operational program that's been driven by the Great Barrier Reef Marine Park Authority. So the platform starts with the CSIP information system to underpin the sharing and distribution of field-derived and modelled data between the control program, CSIP researchers and on-water operators. This is designed to increase efficiency, but also to supercharge innovation across CSIP by making both data and models easily shareable and reusable. That way, if I come up with a better way of estimating COTS density today, my colleagues at UQ might be able to incorporate that into their reef-scale modelling next week, and it might be improving decisions being made at Gurumpa next month. It also provides a direct path for results, path to managers for research results from across the COTS Control Innovation Program. So the information system is work that's been led by Oman Rezvani from CSIRO and myself. We designed and built the information system to provide a federated data store, fully searchable metadata, a process register to track provenance of models, and to track models, and a provenance system to track how that derived data was being generated by those models. Our system incorporates ideas that you will have seen in the RRAP Modelling and Decision Support Information System, and it's also aligned with the RIMREP data management system. But it's a quick and lightweight version built on the Microsoft stack, so it's integrated into Teams, and it can connect into the Power BI dashboards that Gurumpa use to inform decisions in the COTS control program. One of the reasons that an information system is important beyond efficiency is because it enables innovation multiplication through reusable digital workflows, where input data that flows into the information system is automatically processed to become the intermediate and output data that researchers and managers need. The simplest example of this is just the way that we clean COTS control program data as it comes into the system. So this is a task that we used to do manually, but as the program and the data it's collected has scaled up, that's become a bottleneck. To resolve this, Ethan Waters at JCU has implemented a cutting-edge data cleaning system as a reusable digital workflow that sits within the information system. So every time a new tranche of COTS control program data gets put into the information system, the reusable workflow runs, automatically generates the clean data set, uploads it to the information system along with the metadata and the provenance information that's required to understand it and make use of it. So that's a simple example, but the same underlying process enables more complex things like running algorithms to assign man-to-toes to sites or estimating COTS density from control program data. It also forms a foundation for more advanced analyses, such as the way we are adaptively optimising the control program structure by empirically analysing data from the control program itself. And this is work that Carla Yules at JCU has been leading. She's provided a couple of empirical analyses, but I'll just highlight two here. The frequency with which we need to remantotow reefs to make good decisions about where to drop divers, and how we can estimate how much effort a reef should take to bring down to the ecological threshold. These both represent adaptive management based on empirical analysis, in the sense that when we designed the ecological underpinning of the control program back in 2018, we had to make a few simplifying assumptions and take a few educated guesses at reasonable parameters for that system. So one of those was that each reef would need to be mantotowed every fourth voyage, or roughly every 50 to 60 days. And another one was that once we started culling at a reef, we would keep going back to that reef until the job was done, no matter how that transpired. Both of those decisions were based on our best knowledge at the time, but we recognised as we were designing that system that once the control program was running, it would start collecting the data we needed to actually be able to make those decisions scientifically and optimally. And so that's what we've been doing now. Carla's produced an analysis that shows how the quality of decisions about which site to cull at next around a reef declines with the time since the last mantotow at that reef was conducted. As you'd expect, the prediction gets worse with time, and then Carla's calculated how that affects the quality of the decisions that are made. How often does it lead to the wrong site being selected next for COTS control? With the time since last mantotow, which then informs when you need to do a new mantotow so that your decisions are as good as they can be. It's more complex than that simple cartoon makes it look. The answer depends on ecological characteristics of the reef, how recently sites near the site that you're most interested in have recently been culled, and the overall proportion of sites at the reef being culled. And so it's built into a decision support tool that Gurumpa can use to make informed decisions about when a reef needs to be remantotowed. Carla's also produced an empirical analysis of the amount of time we would expect a reef to take to be brought to the ecological threshold when we first arrive at that reef. This is important because although most reefs are relatively well behaved, occasionally the control program encounters a reef that seems to take forever to reduce to the ecological threshold. And when we just persist at these reefs, they soak up a huge amount of resources and prevent us working at and saving coral at other nearby priority reefs. So Carla's produced a statistical model that for each reef that the control program visits takes a few key ecological characteristics of that reef and the initial densities during mantotow and the first culls conducted at that reef, and estimates how much effort it's going to take to bring that reef down to the ecological threshold of COTS density. That's important because it'll help Gurumpa make decisions both about that help them sequence their operations on water if they know how long they're going to have to be working in a given location. But more importantly, it's going to help them identify when a reef is not behaving as you would normally expect, and to use that information to either change their strategy or redirect those resources to other nearby priority reefs. So all that data sharing and reusable workflows and empirical analysis is great, but it's not useful until it makes its way back to managers where they can use it to make more effective decisions. This is exactly the role that Ethan Waters, with a different hat on, has been filling for the past 6 months as our research translation lead in CSIP. He's been working across 3 organisations now, Gurumpa, CSIRO and JCU, and he's been working closely with the other CSIP partners. He literally comes and sits with me 2 days a week at CSIRO, and then goes and sits at Gurumpa 2 days a week with Sam Matthews and the COTS team. He's connected research outputs from the information system sitting on CSIRO computers to the Power BI dashboards sitting on the desktops of Gurumpa computers in front of decision makers as they're making decisions. And then he's talked to them about them, and then he's tweaked them to make sure that they're presenting the information that they need to make the decisions they need to make. So this has been crucial for creating a direct path to impact for CSIP research, such as putting the outputs of the regional or GBR scale modelling scenarios on computer screens in front of Gurumpa decision makers and allowing them to then interact with the outputs so that they can understand and interpret the results. So this is work that comes out of project CSIP-R-04, that Tina Skinner from UQ and Scott Condie at CSIRO have used GBR scale ecosystem models to look at different distributions of the COTS fleet across the GBR and look at the long-term trajectories of coral cover in response to those different strategies. And then there's another dashboard, which isn't shown here, from Gabriela Scheufele's work in CSIP-R-06 that looks at the cost-benefit, the cost-effectiveness of these different strategies. So these dashboards are focused on the decisions that managers need to make, generally in the relatively near term. And sometimes a single CSIP project provides that information. Other times we need to combine the outputs of multiple CSIP projects and other data sets from across the GBR. So a good example of this is the early warning system that Sam Matthews at Gurumpa has developed and Ethan is now helping extend. And this brings in new monitoring methods being developed by Morgan Pratchett and his team at JCU, and Sven Yuthicki and his team at AIMS, connectivity modelling data being produced by Severine Choukroun and Mike Bode at JCU and QUT respectively, alongside other data sources such as the QPWS Field Management Program and AIMS Long-Term Monitoring Program data. The tool aggregates and synthesises data streams to assess primary outbreak risk and help managers make decisions about where to focus effort in response to new outbreaks. Finally, we have our on-water decision support tool. Simply put, this takes all the control program data collected up to yesterday and helps on-water crews make decisions about where they should drop divers in the water today. The tool uses a hybrid architecture that combines cloud-based historical data sharing with local cleaning and integration of voyage data. It runs a COTS density estimation module and provides a platform-independent user interface that can run on tablets or laptops to provide decision recommendations to on-water crews. Like everything else I've been talking about today, the tool is of use in and of itself, but the real power here is that it's connected into this decision support platform extensively. So it's connected to the information system. It reuses code from the reusable digital workflows, and it is modular, so the COTS density prediction algorithm can be updated remotely as new research improves our ability to make predictions about where COTS are likely to be around reefs. For instance, there's a talk in about an hour in one of the parallel sessions where Zahid Islam, who's a research scientist that I work with at CSIRO, and I have developed machine learning methods of predicting COTS densities around reefs without requiring mandatos. So in future, we could integrate that workflow into our algorithm and push it to the decision support app seamlessly. So that's the integrated platform we've developed for information sharing and empirical analysis to innovate decision making for managers and on-water crews in the COTS control program. Right now we have all of these components built and we're in the process of rolling them out. The platform approach I think is important because it provides a direct link between the control program and researchers and then back to control program decision makers. And it provides a direct path to impact for the 20-something other CSIP projects to managers. It helps coordinate efforts to multiply innovation across a large multi-organisational research program by promoting science and code reuse and collaborative connections. And I think probably one of the really standout successes has been Ethan Waters' role as the research translation lead in the last 6 months, which has really allowed us to target and interpret and fine-tune our science outputs to exactly the information that managers need to make their decisions. So my hope is that this kind of collaborative, decision-focused platform approach will continue to underpin great decision-making for the COTS control program and hopefully be extended for other challenges on the GBR. Thank you very much.
Thank you, Cam. We got time for 1 or 2 questions. No questions? Online? No. We don't have it. Okay. Well, thank you, Cam. You make it sound so easy, but I bet it took a lot of time to get there. Thank you. All right, so next we're going to have Gabriela Scheufele.
That's fine, yeah.
Sorry. My bad.
Nobody knows how to pronounce that. That's all good. Thank you very much.
Well, you can tell us how.
Yeah. So how do I give someone? Just the queen, I guess, yeah. Hello, everybody. I would like to begin by acknowledging the traditional owners of the country we are all meeting on today and pay my respect to their elders past, present, and emerging. So what I'm going to present today in my talk is an overview of the economic assessment framework that was developed under RRAP and customized also to CSIP. And that's used to assess different management intervention and strategies that support the resilience of the GBR. So the management intervention explored under RRAP include, for example, the use of aquaculture or moving corals, and the management strategies assessed within CSIP will focus on alternative manual cost control strategies. So it's very important to know that any assessment that's done within that framework looks at the gain of an intervention relative to a counterfactual. So we always look at the difference between a counterfactual and a management strategy or intervention. So we're not looking at absolutes. Okay, let's dive in. So the economic assessment is tightly linked to a lot of other models that produce outputs that use our inputs into our economic modeling work. So let me walk you through them. So the heart of the model data that produces outputs that's really important for us, or where our models really are based on, ecological models, and more specifically ReefMod. So we use ReefMod outputs, and ReefMod modeling is informed by a range of environmental models and data, as well as, of course, data on the interventions or strategies that are being used. Then the data that comes from ReefMod, which is coral outputs, coral outcomes of different ways how it's measured, then feed into what we call coral to benefit translation models that produce indicators. And these indicators are then used in benefit models that predict or estimate benefits over a certain time frame for different streams. So we have non-use benefits. It's, for example, the value people attach to knowing that the Great Barrier Reef exists for a certain time period. And then there's also use values like tourism benefits associated with snorkeling and diving for commercial operators, or fishing benefits related to commercial, charter, or recreational fishing. Then the outputs of these benefit models can then be used in a cost-benefit analysis. So we're looking at what's the social net benefit of a certain interventional strategy, or into an economic impact analysis of outputs. So how many jobs or revenue do we generate by having that intervention that saves us from losing, for example, commercial fishing profits? Then we also have cost data, which is generated through cost models. And the data from the cost models then feeds again into the cost-benefit analysis and into the economic impact analysis of inputs. So how many jobs do we generate by deploying aquaculture and moving these corals onto the reef, for example? So that's mainly for RRAP. And then finally, the coral outcomes directly from ReefMod, but also the indicators then can be used in a cost-effectiveness analysis. So where we look, for example, is how much does it cost to save an additional square kilometers of reef, given a certain strategy under CSIP. So now, and then all of these outputs then can flow into a trade-off analysis, and that can also take other outputs of other metrics or objectives to compare different strategies or interventions. So now what I want to talk a little bit today about is taking just some components of that big assessment framework, mainly cost effectiveness, production possibility, frontiers, and trade-off analysis, at the example of the performance of alternative COTS culling strategies over a time frame from 2019 to 2050. So that's modeled by ReefMod and then feed into our cost effectiveness models. The performance here is measured by 3 indicators. So we have coral area saved in hectare, we have a number of outbreaking reefs avoided, and COTS densities. And the effort is translated into costs in terms of dollars. Okay, so the manual COTS control is implemented in ReefMod as closely as possible to the current COTS control program. And if you have any questions about that, please ask Tina. She or attend tomorrow's talk at 1:30. She will talk about that a little bit further. And then, so we assessed so far 16 strategies. There's 3 more to come. So again, if you're interested in more of this, Tina will talk about very exciting news about the additional 3 strategies which are not yet implemented in this assessment. So we have a group of spatial strategies. The first group is regional strategies. So we will basically have where do we apply the effort? So where do the divers go? Do they go across the whole GBR, which is imitates closely what's currently happening in the COTS control program, so that's SGBR, and then any other variation of a regional focus or combination of different subregions. Then we have another spatial group, that's protection status, where we look at applying GBR-wide effort, but the one scenario is that only extractive use zones, and the other one is any but extractive use zones, to see if that makes an impact. And the third spatial group is following the outbreak front. So there we have 3 sub-strategies, depending on what the guiding principle is on where we apply the effort. So the first one is the guiding principle is priority reefs first. The second one is looking by highest density of COTS, and the third is a combination of the two. And finally, we have 2 effort sink scenarios. So basically, when we find more than 3 COTS per tow, then we don't cull that reef. The first one and the second one, it's the same rule, but if we have a very high coral cover by more than 20%, we still cull it to the threshold. Okay, so if you want to know more about the design and the implementation of these control scenarios into ReefMod, please attend Tina's talk tomorrow. Okay, now let's have a look at some of the results. So we have these 16 scenarios, and this slide just shows you, if you look at the 3 different metrics, coral area, outbreaking reefs, and COTS density, and looking at the annual averages across that time horizon from 2019 to 2050, we see the following. So the best strategies in terms of coral area would be the GBR-wide, followed by the 2 effort sink scenarios. And the worst one would be one of the outbreak front scenarios. This picture really changes when we look at avoiding outbreaking reefs. We see that suddenly the far north strategies of focusing all the effort in the far north is the best, and the worst would be, among others, the another outbreaking front scenario. And again, it looks very different when we look at COTS densities. So now the best one is that which was the worst one under the maximizing coral area, and vice versa. So it really matters of what metrics you're looking at. So now if we look at cost effectiveness ratios, so coral area per $1,000 in this case, so what we can observe is that at the start, it's a really poor performance in terms, it's very expensive. But then it rises very quickly up, it plateaus on the early 30s, and then it sort of declines again in the mid 40s. So it's a very steep curve going up, so cost effectiveness improves over time to a certain point. And this is a trend that's observed across all strategies. Now, if we calculate these ratios for all scenarios, we can see like the best strategy is, of course, the GBR-wide one, because we apply the same amount of effort across all scenarios. You can see that it costs about $2,340 per square kilometer per hectare of coral reef we're saving for the best strategy. The worst strategy, if we apply that, so if we assume that effort increases linearly and the gain increases in a linear fashion, that we would, if we applied the worst strategy compared to the GBR-wide strategy, we would have to pay $23 million more per year. And that's not discounted. So choosing the right strategy really matters. So now we can also have a look at relative cost effectiveness scores. So here we're basically setting the best strategy to 1 and then can see the percentage of performance across the other strategies. So for example, the regional central-south strategy only produces 50% of what the GBR-wide strategy would produce. And we can do the same for maximizing against outbreaking reefs avoided and COTS density. So we get very different results. We also had a look whether it differs, whether we include all reefs or only priority reefs into that assessment. And when we after maximizing coral area, that really doesn't make a difference. And we also looked at some like the simulations that come from ReefMod. So for each scenario and each time step, we get 20 simulations. So that's the distribution of the simulations, and we did some statistical analysis. And all the strategies that have a green tick basically indicate that they are the best strategies, and they are not different from each other, but different from all other strategy on that slide. Okay, so now back to outbreaking reefs avoided. So here we do indeed see that if we only focus on priority reefs, that we would choose a different strategy if we want to maximize avoiding outbreaking reefs. And again, we looked at distributions. Again, those with green ticks are the best ones, and they are not statistically different from each other, but from all other strategies. And here you can also see, if you look at the first green tick, the OFAR strategy has a very wide distribution, so much more uncertain than, for example, the far north RFN, the third one. Okay, so now another thing I want to present here, what's possible with our toolbox, is to construct a production possibility frontier. So what's that? So a production possibility frontier basically shows you two products and then shows you the maximum output you can generate. So everything that's on the line is productively efficient, and everything that's to the left of the line is not efficient, so you could do better. So and then what we can do is we can show, okay, what's the trade-off of producing, using the far north strategy compared to the GBR-wide strategy. So what we're seeing here is if we implement the far north strategy, we're basically sacrificing 58,000 hectares of coral reef saved, but gain about 1,200 outbreaking reefs. So by choosing, because of scarcity, we can't patrol or cull all reefs. We have to make choices, and these choices have consequences in terms of opportunity cost, which in the case of these two alternative strategies is 47 hectare per outbreaking reef. So what if we decide, or we want to maximize against two goals, so coral area saved and outbreaking reefs avoided? We can do that as well, and we see the results for that. So there's 5 strategies that are equally productively efficient, but again, they still imply this opportunity cost, depending on what you choose. So this productive efficiency says nothing about allocative efficiency, meaning what do people actually value. This analysis assumes that they all have equal preferences attached to them, so values equally distributed. So attaching these values, that would be the step of a cost-benefit analysis where that gets introduced. So in conclusion, it matters what metrics you optimize against, and there are trade-offs involved. It matters if you focus just on priority reefs or on all reefs, if you maximize for coral cover, and if you want to maximize against the both goals, the GBR-wide strategy still looks like be one of the best. And if you're just interested in coral area saved, at the moment, the GBR-wide strategy is the best, but it might change when Tina gives me the data for the additional 3 strategies. Something else might come out. Okay, that's all from me. Thanks very much.
Thank you, Gabriela. Any questions for Gabriela? Barbara?
That's okay. Nobody knows. It's fine. Just do your best.
Gabby, did all your scenarios assume that the investment was consistent over time, or?
Yes.
Okay.
Yeah, it's a fixed budget of dive hours. Yes.
It would be interesting to look at the effects of, say, a political interruption to funding or something like that. Yeah.
Would be interesting to do. So if would need to coordinate with the Reef Mod people here if they're willing to run more scenarios. But yeah, no, that would be interesting. Yes. Yeah. Yeah.
We did interpret some of the model runs back during this when we were still trying to get a long-run program up. Interpret it through that lens.
Yeah, and we also had to make some simplifying assumptions regarding the cost. So the costs per dive are the same across all scenarios, which is probably not true. If you're going far north, it's probably more expensive, but the relative cost of going further out really are pale against the total cost of doing that. So I don't think it's worth the effort actually making that more explicit and spending much time and money on getting the cost model more differentiated, but something to think about. Yeah. Yes.
Great presentation, Gabby.
Thank you.
Question on the allocative efficiency.
Yeah.
Is there a pathway for expanding to that dimension, that lens in the COTS space?
It's underway. Okay. It's just not finalized, but next 6 weeks and we have to find a report, by then we'll be done.
Cool. No pressure.
No pressure, no, but that's definitely an important step. Yeah.
Great. Thank you very much, Gabby.
Thank you.
All right, next we have Laura Blamey.
Hi everyone. I am presenting this work on behalf of my colleague Jacob Rogers, who is unable to be here today, and also the next lead after Jacob, Eva Plagani, who's also unable to be here today. Jacob is online though, so he's probably best placed to answer most questions, but I'll endeavour to do my best and also to try and represent the work that he has been leading over the last couple of years. So again, this work also forms part of the COTS Control Innovation Program. We've just heard from Gabby and from Cam before then. Before I begin, just really to also acknowledge the traditional owners of the lands that we're currently meeting on, and pay respects to sort of elders past, present and emerging. So as you're all fully aware, we are dealing with a very large ecosystem, the Great Barrier Reef. It extends just under 350,000 square kilometers, more than about 3,000 individual reefs, and there are possibly thousands, hundreds of thousands of starfish on any given reef. And starfish are culled individually. So there's this big mismatch of scale. We have limited resources to be able to do this, and they don't match the scale of the reef. So how do we maximize the impact with what we've got? So I'm going to be talking about a reef-scale model that we've developed to sort of look at the efficacy of the COTS control program. The main objective of this program is to limit coral loss due to predation by COTS themselves. And the work that Jacob has been leading has sort of, looked at this in different ways. The first was to think about these ecological thresholds that sort of underpin those cull per unit effort targets, and refine these by, sort of considering sort of local factors, things like different coral growth rates, which we know might vary across the GBR, and due to other impacts like climate change. Also to evaluate the relative performance of different intervention strategies for COTS control, and this specifically is not at a regional scale that I'm talking about, but rather at sort of a management site scale. And then also characterize when or where different interventions might be most effective in limiting COTS impacts at these sites. So the ecological modelling approach that Jacob has used, and one that I've worked on as well elsewhere, is these things called MICE models, or models of intermediate complexity for ecosystem assessment. Essentially, they try and find that sweet spot in the modelling world of complexity. So between really simple models that might just consider, one or two species, to these really whole of ecosystem models that are really complex in the number of species and the parameters that they contain. The nice thing about these MICE models is that they're custom designed to the ecosystem that they are, that we're targeting. They just focus on sort of those key components of a system. They are fitted to data, and they use sort of, I guess, statistical fitting techniques and different ways of sort of, identifying your best modelling, sort of your best model to try and be able to then also address some of these management questions. They can also have, sort of the environmental impacts included into them. They can have human dimensions brought in as well, and they can account for a range of uncertainties too. These MICE models are sort of not really a new approach. They have been around for a while. They've been used in different systems, for example, to try and better understand the impacts of harvesting water from rivers on downstream fisheries and ecosystems in the Gulf of Carpentaria. They've been used to better understand changes in temperate reef ecosystems in the South Atlantic. They've also been used to better understand climate change on recovery of baleen whales in the Southern Ocean. So without going into sort of the details of this actual model itself, this is really just a snapshot of what's in there. We have sort of some background recruitment that comes into the model, and is then sort of, we have this age-structured COTS component and 2 different coral components, sort of a slow-growing, less preferred coral, like your Porites species, and then this fast-growing, more preferred for COTS, things like your Acropora species. And we have sort of different interactions between the COTS and the coral themselves, and these feedback loops as well. Things like prey switching when your preferred coral cover declines and that sort of thing. We can also account for external, impacts, things like your cyclones, coral bleaching as well. And importantly, what this model is founded on is that it's fitted to these data. So we bring in things like your cull data, your dive time, your catch per unit effort, your total number of COTS that are culled, and total coral cover. So the model is validated on past data and then is used to sort of compare different scenarios. Some of the early work that Eva Plagani led was sort of defining these ecological thresholds. She did this using a steady state analysis, which took a version of this mice model and really looked at, okay, where is this equilibrium point where coral growth is balanced by the amount of coral eaten? Coral growth is balanced by the amount of coral eaten, and where we find that there's that no change in coral, what are the number of COTS that are, allowing for that equilibrium state? And that can be then converted into this sort of expected catch per unit effort or cull per unit effort that we would want from that reef. Jacob's work's then gone on to sort of refine this a bit and has looked at, okay, how might these control targets change depending on sort of geographical area or different impacts of climate change. So thinking about, in this case, he used an example of if coral growth increased or decreased, how might we expect these ecological targets to change? So he modeled differences in growth rate of the corals relative to the original threshold. And if you look at all those sort of pretty colored curvy lines on that plot on the right, that's really just showing the different points of equilibrium for those different growth rates. And really what we found was those equilibrium points were quite similar under different coral growth rates for lower levels of coral cover, but not necessarily, it was slightly more nuanced when you got to higher levels of coral cover, and it really depended then on what sort of your objectives were. Again, I'm not going to go into the details of that contour plot on the left there, but it is in a paper that's in review at the moment and will be part of that CSIP report that comes out in about 6 weeks' time. But what he found was that under different growth rates, it really, it made little difference as to what that catch per unit effort threshold was for coral cover up to about 40%. And that difference was really, really small when you had those low levels of coral cover, sort of less than 1 COTS per dive. And that typically the current thresholds that are being used are pretty robust to different coral growth rates for that lower scale of coral cover. This sort of aligned with other work that Jacob had previously done, where he found that the current thresholds, were better than using sort of more or sort of lower threshold targets. The next thing that we looked at was, can management improve coral recovery under outbreaking conditions? Sorry, this is actually Jacob's previous work, not part of the CSIRO project, but really what he was looking at, if we simulate these outbreak conditions using a mice model and we run these different management scenarios, do we see a difference in which scenario might perform better in terms of coral cover and catch per unit effort? So some of the scenarios he had was sort of that, no control, you do nothing, versus you have sort of some strategic control or versus a random control, or you use these thresholds to help dictate where about you're going to perform that control and across different voyage intervals. So if we look at the plots over here, the top left plot just shows the difference in coral cover, and the bottom is that the COTS catch rate. And what he found was that frequent voyages were best. So if you had to go sort of every 2 weeks compared to every 10 weeks, And these frequent voyages were able to reduce the COTS faster back to non-outbreak levels, sort of, 2 to 4 years earlier than if you had not been doing frequent voyages. And that's these threshold-based approaches were better placed by using, the latest information than rather going for some sort of random site selection or a strategic site selection. And this sort of one of the spin-offs of this work was, sort of coming to the notion of what's now sort of commonly known, I guess, as these effort sinks, is that a reef or site that's using up a lot of time that then can't be used elsewhere. And there are various reasons for this, one of them being limited resources, others that there might just be lots of COTS on that reef, or there might be sort of these low coral or CPU targets that divers are trying to achieve. And then just lastly, just to talk about some of the other work that he's been doing is to evaluate control efficacy at the site level. So this work sort of looked at the historical approach of control, sort of I think it was 2018 versus this decision tree approach. The left-hand graph just shows the relative change in coral cover, the average change, and the right-hand graph there is sort of the median of that. And really what he found was that the decision tree approach sort of consistently outperformed that historical approach, and up to about 70% of more coral was saved per minute, plus the number of dive hours used was a lot less under the decision tree approach. It was also more consistent across sites, and however, it might have greater risk to sort of things like these bleaching events. And that's really just because there's more coral that has been saved, and so then there's more coral that could be lost under bleaching. He's also taken this another step further and added in new data, and has, sort of doubled the number of reefs that he now fits the data to, and a lot more sites, and has compared sort of the actual control that's used versus no control, and found that there's been a consistent improvement in coral saved per year, up to about sort of 8% on average saved across sites over sort of about 3 years. So what does this mean for management? Because I think at the end of the day, that's really, what we're interested in is what implications does the research have for the management. So I guess just to summarize that uncontrolled scenarios led to lower coral cover compared to controlled scenarios. The current thresholds have found to be fairly robust to variation in coral growth rates. And that these threshold-based approaches performed better than just randomly selecting sites. And then, again, it comes down to what are the objectives. You may need to consider why is a reef prioritized, and possibly when you might not want to attempt controlling a reef. And then also that removing the most COTS doesn't necessarily translate into the most or the best outcomes for coral. And you need to consider both where COTS are recruiting to and where the coral will benefit most. And so far the mice model suggests that this can vary even within a single reef. But because these models are sort of integrated and take into account both coral and COTS at the same time, these tools can help sort of find those nuances and pinpoint to that. I think I'll leave it there. There are some other next steps, but I'm not going to go into those. And thanks very much.
Any questions for Laura? Yes, please.
If I'm allowed another question.
You are.
With the mice models, how do you assess where you are in that curve, whether you're too simple or too complex?
That's a very good question. I think it comes down to we have sort of a structured, I guess, framework approach of I think a mice review paper was put out in about 2014 that provides some of those guidelines. We generally in mice is looking at sort of no more than 10 species, and it's a trade-off between the more species and the more parameters, and you've got to parameterize. So I think there's no one size fits all in terms of what that actually is, but it's really just identifying what are the critical species in that system that we have a question surrounding.
All right, next we have Alejandro Astorga Moar, who's going to be talking from UK. Thank you.
Okay, hello. I'm Alejandro from UQ. I'm a PhD student and also doing a research fellow under the supervision of Tom Baldock. Here we are developing an app to identify vulnerable areas in the Great Barrier Reef where we can do interventions or restoration projects. I was going to talk about the GBR, but I think you are more familiar than what I could be, at least under your background. Mine is on engineering. So we know about the threats. We're facing climate change, and that's one of the reasons why we're developing this app. So we need a decision tool to identify these kind of areas where we can do something. But we also need these kind of tools to put it in public, so any user, no matter the skills they have, they can use it. But also it could be useful for decision makers or even for other tools like the ones that they are developing at the Marine Science Lab with Peter and you. I forgot your name, sorry. But anyway, so we're basically working with 3 variables. The first one is bathymetry. So we have the information of the elevation or the depth in the Great Barrier Reef, and that's allocated in more than 300 patches. Basically, what we have here is at least one reef. It could be more, but in average, I guess we have like 10 reefs in each patch, and those are represented in the blue boxes. So that's the first variable we need. The second variable that we need to know these vulnerable areas are the wave head and the wave period. And this data comes from numerical modeling from Dave Callaghan, also at UQ. So he ran a model through all the Great Barrier Reef to get the wave climate along the system. But it's a lot of information because each pixel of the bathymetry is 25 meters by 25 meters. And inside there, we have the joint probability of wave head and wave period. So that's quite a lot. And that's why another reason why to have a decision tool, because that will make things easier for final users. So basically what we have here in colors, if we have warmer colors, that's the most probable scenario that we can have. So we can have combinations of wave head and wave period, and we will have a specific probability for that event. And why do we need that? So we can characterize the bottom wave velocities by using the wave height. In this case, is h. And the wave period is represented through the omega, for the wave frequency. I forgot the name, sorry. And we also have included the wave depth. The depth as h. So these 3 variables are necessary to calculate the velocity using wave linear theory. And it has shown that this approximation is useful for coral reef environments. So as an example, I'm showing you this. So we have this wave climate or typical conditions as TP typical and HC typical. So we can calculate the velocity from this. But also we can calculate the maximum conditions, and we can locate that by taking the maximum value of the wave head. We can get it from this distribution. Another thing that we need for our model or this platform that we are developing is the probability of failure for corals. So this work has done by PhD students. So what they did, they took samples in the field. So they removed the corals. They measured the force that he needs to be applied to be broken. And they did the same in the lab. So at the end, what has been done is a structural model in which they did thousands of simulations with different velocities. So this force can be translated into velocity. So they force this structure or coral structures. And what we got, or the PhD student got, is this plot on the left side of probability depending on the wave velocity. So we have in the x-axis the velocity, and on the y-axis how probable it could be to break under certain flow velocities. This model also was used with different bioerosion rates. So what we did here is choose 3 locations in which we can have bioerosion in the coral structure. And for these 3 scenarios, we have certain biodegradation values. So this is in progress, but we expect to include this bioerosion in our tool soon. And finally, we also have the probability of robot mobilization, which was done by Tanya Kenyon. Here, this project was done through field and laboratory experiments, and it was done with different type of corals, robots. So in this part, we're talking about robots, so we're interested in knowing how robots move through the coral reef. So for this, Tanya Kenyon did some laboratory and field experiments with branched corals, which are in the left side, and not branched corals, which are on the right side, for different sizes, which are represented in different colors in this plot, for different for different floors. So one of the floors had robots in the bottom, another one just with sand. And these are the final colors we got, and those were included in the model. So what we have now is an interface that could be useful for anyone. So in the left side, we have the input parameters we want to know or to include in the model. So we can calculate the probabilities of breakup and motion of robots by choosing first the location of the reef. So we can input that in the left side, or we can click into the map and extract the coordinates with the button that is like in the middle of the screen. We can choose the parameters we want to choose, which will include wave height, typical, and we expect to add more scenarios like return periods. And after that, we have in the input panel, solid fraction panel. I'm not sure if it's visible for you. It's shown in the red circle. So in that part, we can choose the parameter for the breaking model, or for the breaking model, in which we can choose the location of the bioerosion, the rate of bioerosion, but also we can choose the size of the colony that we want to study on. And then we have the robot mobilization panel. And here we can choose, following what Tanya did, we can choose the size, what kind of motion we want to follow. So we have 3 options: rocking, transport, and flipping. What kind of robot we want to study, which is branch and unbranch, and in which kind of substrate the robot could be located. And the right side is where we can visualize all the Great Barrier Reef, but also the results. For example, for example, we have, in this case, we have the bathymetric, which is data that is already in the system. And this is one of the results. So this is the distribution of the wave height according to the scenario we chose. We also calculate the velocities in the bottom. So that's done through the wave climate and the bathymetry. And this is the breaking probability result. It's mostly in blue because, I mean, it depends on the wave conditions. And there's where we can find like the vulnerable areas will be like really small areas. And we have the result for mobility probability. So we are also working on getting the outputs in different formats. At this moment, we can do it through TIFF file, TIFF file, but also as image or .fig, which is for MATLAB. So we are also working in a user manual that works with HTML format. And what we want to improve in the future is to migrate from the language we're using, because we're working with MATLAB, and apparently it's really hard to work with geospatial information there. So we expect to move maybe to Java or Python, which will be also useful for anyone because it's a free, an open source system or language. We are also expecting to add a numerical model, which is XBridge, and it's been applied to coral reef environments. And yeah, we want to include this model into the system. And yeah, that's all I have for today.
Thank you, Alejandro. Any questions for Alejandro? Just have a quick one. Have you considered changing by erosion over time in your model?
No, we haven't. So we're working with all the data we have from previous numerical information. So if that's the case, we might need to be updating all the wave climate information. Sure. But yeah, we haven't done this to be dynamic, like changing on time, okay. But maybe it could be a future improvement.
Okay, thank you. Any further questions? No? All right, thank you, Alejandro. The last of our presenters has submitted a pre-recorded session. So this is Karen Chong-Seng from the Reef Authority. Is that all right to play? Thank you.
Hi, I'm Karen Chong-Seng, and I'm a data analyst in the Science for Management section at the Reef Authority. Today, I'll be talking about how we've been working to operationalize data provision for decision-making. First, I respectfully acknowledge the traditional owners of the land on which I am presenting today, the Wulguru Kaba and Bindal people in Townsville, as well as the traditional owners across the GBR and its catchment. I pay my respects to their elders past, present, and emerging. The Reef Authority recognises traditional owners as the first scientists of the land and sea, and values their traditional knowledge, which continues to inform the current management and stewardship of the reef. So, operationalizing data provision for decision-making. What does this even mean? For me, it means ensuring that useful data sets, often spatially explicit, are available for use when they are needed and in a format that they're understood. This means that many of these data sets, which also include model outputs, will be used for purposes beyond the original, often very specific aims under which they were collected. As one colleague recently said, the results are transferable to many scenarios. Why is this bit important? It's because reef managers, ourselves as the Reef Authority, traditional owners and other government agencies, have to make decisions every day to the best of our abilities, irrespective of what data and information is at our fingertips at the time, about who can do what, where and when, about which things money, time, and human resources will be spent on. Most of the time, it boils down to conflicts in values and use. Where do important processes on the reef intersect with important uses of the reef? That data gets used beyond its original scope is also important, because for many of those decisions, we don't have a dedicated team of researchers on hand, available to help, and this is where knowledge brokerage comes into play. So knowledge brokerage. Some of you may have listened to Cindy Hutchery's talk during the 2022 Social Science for the Reef Symposium. It's all of 10 minutes long and well worth a watch. The conclusion is that there is actually no bridge to cross between science and management. While our constraints might be different, our goals are the same. So we really are standing together on one side with a problem, in this context, a decision that needs making, trying to build or cross a bridge towards a solution, a decision that is based on the best available evidence. Not every project needs to be highly collaborative, but starting from the same place is important. This session promised to be an interesting and exciting mix and overview thinking with proper decision support tools through to detailed ways that knowledge brokerage has occurred successfully, especially in the prioritization of COTS control implementation areas. The Reef Authority also engages in knowledge brokerage in other areas, and the Science for Management section's purpose is to support the long-term protection and conservation of the reef by facilitating access to and communication of science and knowledge for effective reef management. We have three broad groups of activities. First, we broker, collect, and engage with the scientific community, partners, and stakeholders, focusing on increasing the agency's access to knowledge about the reef and working to ensure strong coordinated partnerships between the science and management community. Secondly, we synthesize, analyze, and share data and information, which is also about focusing on the agency's access to knowledge, but in a data literacy context. Data can be interpreted and contextualized for new purposes, and ensuring strong partnerships. Many of us have research backgrounds and know the value of involving data providers when using new data sets for the first time. Caveats, potential limitations, factors to take into consideration are all important. Finally, decision support, a collaborative approach to ensure the best available information is used to inform resilience-based management of the reef, working on bespoke products with individual teams on specific questions. So, resilience-based management at the Reef Authority takes place within the context of the Great Barrier Reef Marine Park Act from 1975, which established the Reef Authority, broadly aiming to preserve the region's values. In 2015, the Australian and Queensland governments released the Reef 2050 Long-Term Sustainability Plan, which is the framework that partners collaborate on to make our management most effective. RIMREP, the Reef 2050 Integrated Monitoring and Reporting Program, is a partnership between multiple agencies, ensuring that the science and knowledge collated through Outlook is driving our management responses. And there'll be a presentation about this during the conference at 10:45 tomorrow in the Urchins Room. This diagram explains how it works. It starts with our objectives and management needs, articulated by the Reef 2050 plan, and ends with evidence-based management. In the middle are the three sections where our work focuses. Collect is where we gather data and information. Access is the behind-the-scenes data engineering to provide access and connect data streams. And Show is where we do reporting, creating data visualization and decision support tools, which are all made available on our online portal called the Reef Knowledge System. So back to operationalizing data for decision making. Some work we've been doing has focused on providing situational awareness, in this case, primarily the physical and environmental context within which decisions are being made on the reef. It builds on some work done to assess cumulative impact. In this case, thermal stress, cyclones, Crown-of-Thorns starfish, freshwater runoff, and combining them into an index of exposure. How do we make these products accessible to decision makers and, importantly, up to date? These analyses need rerunning annually and after major events. So also, considering just the index on its own, the reefs in the region could be ranked from good to bad, but if, for example, a permit assessor wanted to evaluate the pros and cons of allowing collection at a reef or giving the green light to a pilot restoration project, it would be much more informative to be able to interrogate the data set that sat behind the index. So this is now when I introduce the Resilient Reefs Network guidance tool. So currently proof of concept stage, so it's not targeted or tailored towards specific decision making. So to be a proper decision support tool, it would need to be tailored towards answering specific questions. This view shows whole of reef level information. So there's different aspects of situational awareness. There are the individual pressures, which can be considered bronze or raw data sets in data engineering speak. In this case, showing the cyclones that cross in the 2013 and 14 summer, an estimate of cumulative exposure and recovery potential, both silver or analyzed data sets, and the combination of both into one index of resilience potential, a gold level data set, one underpinning a published product. There are several ways to calculate this resilience potential, and depending on the specific question, a knowledge broker would be able to provide guidance around known caveats and limitations. Data can also be viewed and interrogated for individual reefs. So going back to my previous example about a permits assessor, this dashboard shows how much physical impact a reef has experienced through time. If it were recently disturbed, then allowing collections is probably not the wisest choice. For more reef, which you'll be visiting at the end of the reef, it shows exposure to thermal stress, cyclones, and Crown-of-Thorns starfish. If it's about a restoration project, using the wave model to highlight where on the reef strong waves are likely to come from might be valuable. Permit assessors are kings and queens of scenarios. Each assessment must consider 14 separate mandatory considerations which are detailed in the Reef Authority regulations. These include biological impacts, cultural impacts, policy and legislative requirements, and orderly and proper management of the marine park. This tool only considers biological impacts, but also provides some extra filters that can provide context for the others. For example, the zoning, which zoning areas different reefs fall on, whether they're surveyed as part of different monitoring programs, whether they're in upwelling or in different bioregion areas. So this covers what I just said about permit assessors, but also during a permit assessment, each of the 14 considerations requires a different viewpoint, and availability of data that can address these views is highly advantageous. Data relating to resilience, so function, structure, processes, is highly relevant given that it is a core component of resilience-based management. Data assessing potential for damage to ecological and social systems, including cumulative impacts, is vital. Allowing access to verifiable and usable data sources is in everyone's interest, as it allows for more effective assessments and greater understanding of proposed activities. So the bulk of the work for the Resilient Reefs Network guidance tool was done 3 to 5 years ago, and I'm excited to see how many of its core data sets have evolved and developed through the various previous presentations. Yves-Marie's keynote, a much more sophisticated and whole-of-system way of bringing some of these data sets together. All of the coral and COTS larval connectivity work, which I'm looking forward to being able to incorporate. As the way the method was put together, is I hope that it will easily be able to slot new data in. And even the wave models that aren't formally included in assessments, but are present for additional information. As it stands, however, this tool that I just presented is what is accessible by the majority of Reef Authority decision makers on a day-to-day basis. So with that, my key messages. A key barrier to operationalizing evidence-based decision-making has been access to up-to-date data and in a way that is easily interpretable for the decision being made. So let's celebrate the DMS, the RRAP Data Management System, is the next step to actually achieving actual connections to live data sets. And if you would like to make a difference in how your research is incorporated into Reef Authority decision-making, consider making your data sets available through the RRAP Data Management System, and not just your final model outputs, but also your bronze and silver data layers, the data sets that underpin the final results and outputs. They are so valuable for providing context and guidance for interpretation uncertainty. Please get in touch, science@gbrmpa.gov.au. And finally, I'd like to plug again the RRAP talk tomorrow at 10:45. Thank you.
Thank you very much, everyone. I believe that I'm new to this session, but I believe we do a wrap up. I was waiting for Mia to help me because I wasn't here in the morning to do a wrap up, but maybe if Maria, you can actually help me summarizing some of that. If that's all right, I'll put you in the spotlight. But first of all, I just want to if you can join me to give a round of applause to the presenters, because they did an amazing job. And it's probably the first time that being a chair, we finish on time, so well done. Yeah, so Yves-Marie, would you have any concluding thoughts of the morning?
Well, to be honest, so I gave a talk in this room in the morning, but then I was...
You had to run.
So I was not always in this place.
Okay.
So I'm not sure I can do a proper wrap-up, but...
Yeah, anyone else that were here in the morning that could actually help me? Because I was in the other session.
I guess something that struck me about the talks this morning is how much good work is being done across CSIP, across different components of RRAP and so forth, and sometimes tackling different aspects of a common question like the connectivity session, and coming together here is really useful so that we can make those connections and learn from each other rather than just working in parallel.
Yeah, no, that's brilliant. Any additional thoughts for that morning session that could actually help complement to that?
I suppose I found that I was really heartened to see, I was really heartened to see the collaborative efforts in this space, and I suppose also heartened to see that the decisions that we're going to make in the future in terms of restoration are being informed by some fantastic models that are in production. Yes. So I thought that was really heartening.
Nice, thank you. Any further thoughts? Rena?
Again, I was in and out throughout the whole day, but I think one of the key things that might be worth discussing is way forward to integrate all those awesome efforts, because while it's really good to learn about some new ones, I think a few of them I already knew were happening for the last few years, and I think integrating across models and across other efforts that are collecting useful data, highlighted by the last talk, would be amazing, and would, the sum of all parts are a lot more than just the sum of all parts. It would really, really help us do what we're doing even better.
Mm-hmm. Thank you. And I think that probably like in the afternoon we started seeing a little bit more of that integration, which is awesome to see. And I think that I just have to reflect a little bit on how the afternoon went, because if we start from the end, from Karen's talk, it's amazing to see also that connection between decisions makers, modelers, and those that are in between to facilitating the delivery of the modeling and decision support. But basically, like, we've been struggling a lot for a long time to trying to make decisions when data is not necessarily readily available. But one of the biggest challenges is not only just having the data readily available, but Cameron was also showing how you can actually transform those data sets into ways that are more management ready, which I think is one of the biggest challenge. And I think, Gabriela, you were also talking about sort of monitorizing and the challenges around that, because, yeah, like, sadly, but politicians only care about money. And we all do. And I think part of that is a kind of understanding what the consequences are of our actions, which is, to me, one of the things that we tend to leave to the last minute. And it's amazing to actually get that into a perspective where we are now joining efforts together into the afternoon. But also, part of this is kind of the worry that we have that we're building such a complex foundation of science in terms of modeling and forecasting our efforts to drive in more efficient management actions into an uncertain future, but without actually having a framework like what Barbara presented, where kind of we have a proper QA, QC of our models, a ways to actually assess in a way that is a standard, that we have a way forward that we trust on and is transparent, but also builds on the reputation of what we're trying to do, so we can move forward in a sequential steps, that we kind of don't build a house of cards without realizing. So I think this last session was actually a really good combination of all these different approaches, that is not only just about the science behind the modeling, but how we put it together, how do we transform data sets into ways that are more management ready, but also how do we trust that? And Karen's way of presenting was beautiful, to actually wrap it up and say, this is how we use it. So you guys did an amazing job. I just summarize that part of the job. So thank you so much for that. And I don't know if you have any additional comments, but otherwise we can just wrap up the session. Good. Thank you.